In the summer of 2007, something happened that would challenge everything we thought we knew about human history, about the rise of civilization, about the very story we've been told since childhood. A geologist named Richard Firestone was drilling into the Arizona desert, taking core samples near a place called Murray Springs, when his equipment hit something unusual. It wasn't rock, wasn't sand, wasn't the expected layers of sediment that had accumulated over thousands of years. It was a thin band of black material, dark as coal, compressed between layers of ancient soil like a bookmark in the pages of Earth's history. Firestone pulled the sample up, examined it under the harsh desert sun, and felt something shift in his understanding of the past. This wasn't ordinary soil, wasn't the result of normal geological processes, wasn't something that should exist in the quiet layers of an Arizona dig site. The black layer was exactly 4 centimeters thick, precisely uniform across the entire excavation area, and, when he measured its age using radiocarbon dating, the results came back with disturbing accuracy. 12,800 years old, give or take a few decades. Not approximate, not roughly around that time period, but exact, as if something had marked that moment in history with deliberate precision. But the age wasn't what made Firestone's hands shake slightly as he held that sample. It was what the black layer contained, what secrets it held compressed within those 4 centimeters of darkness. He sent portions to laboratories across the country, waited for results with growing anticipation, and, when the data came back, it read like something from a disaster movie, not from a scientific dig in the American Southwest. The layer contained massive amounts of carbon black, the kind produced by enormous wildfires, fires so intense and widespread that they would have turned forests into ash across thousands of square miles. That alone would have been remarkable, would have suggested some kind of regional catastrophe, perhaps a period of unusual drought or lightning storms. But there was more, much more. Mixed within that carbon were nanodiamonds, microscopic crystalline structures that only form under conditions of extreme pressure and temperature, the kind of conditions you'd find at the impact site of a meteor strike or in the heart of a nuclear explosion. These weren't the kind of diamonds you could mine naturally, weren't the result of millions of years of geological pressure deep in Earth's crust. They were shock diamonds, formed in an instant, created when carbon is subjected to pressures exceeding 100,000 atmospheres and temperatures above 2,000 degrees Celsius. Firestone's team found something else too, something that made the hair on the back of his neck stand up when he saw the lab results. Iridium, an element so rare in Earth's crust that finding it in any significant quantity is immediately suspicious, was present in concentrations 100 times higher than normal background levels. Iridium is common in asteroids and comets, abundant in the rocks that float through space beyond our atmosphere, but vanishingly scarce on our planet's surface. When geologists find iridium spikes in sediment layers, they know they're looking at evidence of something that came from beyond our world, something that fell from the sky with enough force to leave its signature in the geological record. The presence of these 3 markers together, carbon black and nanodiamonds and iridium, all in the same thin layer, all dated to the same moment 12,800 years ago, pointed to a single, unavoidable conclusion. Something had exploded over North America, something big enough and hot enough to start continent-wide fires, to create shock diamonds from the carbon in burning forests, to leave traces of extraterrestrial material scattered across the landscape. Firestone was looking at evidence of an impact event, a cosmic catastrophe, a moment when something from space had intersected with Earth in the most violent way possible. But here's where the story gets truly extraordinary, where it transitions from interesting scientific discovery to potential evidence of a global cataclysm that reset human civilization. Firestone didn't keep his findings to himself, didn't hoard the data or work in isolation. He reached out to colleagues across North America, asked them to check their own dig sites, to look at sediment layers dated to that same 12,800-year mark, to see if they could find similar evidence. And they did, at site after site, location after location, stretching from California to Pennsylvania, from Canada to Mexico. The black layer wasn't isolated to Arizona, wasn't a local phenomenon, wasn't the result of some regional disaster. It appeared at 29 sites across North America, always at the same depth, always dated to the same moment, always containing the same mix of carbon and nanodiamonds and iridium. Later investigations would expand that number to over 50 sites, and the pattern would spread beyond North America entirely. Researchers found the layer in Syria, in Belgium, in Chile, in sites scattered across 4 continents and spanning nearly half the globe. Whatever had happened 12,800 years ago hadn't been local, hadn't affected just one region or one continent. It had been global. Think about what that means, really let it sink in for a moment. 50 separate locations, spread across thousands of miles, all showing evidence of the same catastrophic event occurring at the same moment in time. Not over decades or centuries, not gradually spread across different time periods, but simultaneously, as if the entire planet had been caught in the blast radius of something so massive that its effects touched nearly every corner of Earth. This wasn't a volcanic eruption, which would leave ash in a regional pattern based on prevailing winds. This wasn't a series of unrelated fires, which wouldn't explain the iridium or the nanodiamonds. This was something else, something that required a different explanation, something that demanded we reconsider what we thought we knew about the world our ancestors inhabited. Firestone and his colleagues published their findings in 2007 in the Proceedings of the National Academy of Sciences, one of the most prestigious scientific journals in the world. The paper was cautious, was measured in its language, was careful not to make claims that couldn't be supported by data. But the implications were clear to anyone who read between the lines of scientific terminology and careful hedging. The researchers were proposing that Earth had been struck by fragments of a comet or asteroid approximately 12,800 years ago, that this impact had triggered massive environmental changes, that it had reshaped the climate and possibly altered the course of human history. The timing, you see, wasn't random. 12,800 years ago corresponds almost exactly with the beginning of a period geologists call the Younger Dryas, a sudden return to Ice Age conditions after the world had been warming steadily for thousands of years. It was as if Earth had been recovering from the last Ice Age, temperatures climbing, glacier retreating, life spreading northward into previously frozen territories, and then suddenly, inexplicably, the planet plunged back into deep freeze. Temperatures in the northern hemisphere dropped by 15 degrees Celsius within the span of just a few years, not gradually over centuries as climate usually changes, but abruptly, catastrophically, fast enough that the generation experiencing it would have noticed the world growing colder around them. This Younger Dryas period lasted for 1,300 years, more than a millennium of bitter cold that shouldn't have happened according to the natural cycles of ice ages and interglacial periods. Scientists had known about the Younger Dryas for decades, had documented it in ice cores drilled from Greenland's glacier, in sediment layers from lake beds, in pollen records that showed forests dying and tundra spreading south. But they'd never been able to explain it adequately, never found a mechanism that could plunge Earth back into Ice Age conditions so quickly and completely. The Comet impact hypothesis provided that mechanism, offered an explanation that fit the evidence with disturbing precision. But Firestone's black layer revealed something even more troubling, something that extended beyond climate science into the realm of biology and extinction. When he examined the sediments immediately below that black layer, below the evidence of cosmic impact and global fires, he found bones. Lots of bones, representing species that had thrived in North America for millions of years, animals that had survived previous ice ages and warm periods, creatures perfectly adapted to the environments they inhabited. There were mammoth bones, from the massive elephant-like creatures that had roamed the continent in herds, giant ground, sloth bones, from animals the size of modern elephants, saber-toothed cat remains from predators with fangs longer than human hands. These species had been abundant immediately before the black layer was deposited, their bones common, in the archaeological record, their presence so constant that finding their remains was routine for paleontologists working in Pleistocene-era sites. But above the black layer, in sediments deposited after that moment 12,800 years ago, their bones disappeared entirely. Not gradually, not showing signs of declining populations over centuries, but completely and suddenly, as if someone had flipped a switch and erased them from existence. 35 genera of large mammals went extinct in North America during this narrow window of time, disappeared from the fossil record within what appears to be a few decades or at most a few generations. This extinction event had been known to science for years, documented and studied and debated by paleontologists who couldn't agree on its cause. Some blamed human hunting, argued that Paleo-Indians had hunted these species to extinction, despite the fact that humans and megafauna had coexisted for thousands of years before without similar extinctions. Others proposed climate change, suggested that the onset of the Younger Dryas had disrupted ecosystems enough to cause widespread die-offs, though this didn't explain why these animals had survived previous climate fluctuations without issue. The Comet impact hypothesis offered a third explanation, one that was immediate and catastrophic enough to account for the speed of the extinctions. Imagine what it would have been like, what that moment might have looked like to any human who witnessed it and survived. You're living in North America 12,800 years ago, part of what archaeologists call the Clovis culture, named after distinctive spear points found at a site in New Mexico. You're a skilled hunter, part of a sophisticated society that has spread across the continent, people who craft beautiful stone tools, who have complex social structures, who have thrived in this Ice Age environment for generations. Your people have developed techniques for hunting mammoths and other megafauna, have established trade networks that span thousands of miles, have created a culture rich enough to leave behind artifacts that still impress archaeologists today. Then one night, or perhaps one morning, the sky begins to glow. Not the normal glow of sunrise, not the familiar light of day breaking over the horizon, but something else, something wrong, something that makes you stop whatever you're doing and stare upward in confusion and growing fear. Streaks of light appear, dozens or hundreds of them, blazing across the sky brighter than any shooting star, growing larger and brighter with each passing second. They're not stars, you realize, not celestial objects peacefully traversing the heavens. They're falling, plummeting toward Earth with terrifying speed, and they're getting closer. The first impacts hit with force beyond anything you've ever experienced, beyond anything your ancestors described in their oldest stories. The shock waves ripple outward, knocking you off your feet if you're close enough, shaking the ground like an earthquake if you're farther away. The sky lights up with fireballs, with explosions occurring in the upper atmosphere as comet fragments hit air, molecules at 60,000 kilometers per hour, as ice and rock and frozen gases superheat and detonate with the force of nuclear weapons. The air itself seems to catch fire, winds of superheated plasma rolling outward from the impact points, igniting everything they touch, turning forests into walls of flame within minutes. If you're far enough from the direct impacts, you might survive the initial blast. You might be able to run, to find shelter in a cave or behind a rock formation, to hide from the thermal pulse that incinerates everything in its path. But then comes the real horror, the long-term consequences that will reshape your world far more dramatically than even the immediate destruction. The fires spread, consume forests across entire regions, fill the sky with smoke so thick that the sun becomes a dim red circle barely visible through the haze. Ash begins to fall like black snow, coating everything, choking animals and humans alike, poisoning water sources, covering the ground so thoroughly that plants can't grow. The temperature begins to drop, not immediately, not in the first days after impact, but within weeks or months as the smoke and ash in the atmosphere block sunlight from reaching Earth's surface. This is what scientists call an impact winter, the same phenomenon that killed the dinosaurs 65 million years ago when a much larger asteroid struck the Yucatan Peninsula. The version that hit 12,800 years ago was smaller, wasn't an extinction-level event for all life on Earth, but it was more than sufficient to plunge the Northern Hemisphere into conditions resembling a nuclear winter. The megafauna, those enormous animals that had dominated North American ecosystems for millions of years, couldn't adapt quickly enough. Mammoths needed vast quantities of vegetation to survive, required hundreds of pounds of plant matter daily to sustain their massive bodies, and when the plants died from lack of sunlight, when the grasslands and forests turned to ash-covered wastelands, the mammoths starved. Saber-toothed cats, which hunted large prey, found their food sources disappearing, found themselves in an ecosystem that couldn't support apex predators of their size. Giant ground sloths, which had been perfectly adapted to their environment for millions of years, discovered that adaptation meant nothing when the environment itself was destroyed in a matter of weeks. And humans, the Clovis people, faced a different kind of extinction. Not complete extinction, not the erasure of the entire species, but the collapse of their culture, the destruction of the complex society they had built over generations. The archaeological record shows this collapse with stark clarity. Below the black layer, Clovis artifacts are common, found at hundreds of sites across North America, evidence of a thriving culture with sophisticated technology and widespread distribution. Above the black layer, Clovis artifacts disappear, vanish from the record as completely as the megafauna they hunted. Archaeologists call this the Clovis barrier, a boundary line in the sediment that marks the end of this culture's existence. Some Clovis people surely survived, must have found ways to endure the impact winter and the climate chaos that followed, because humans continued to inhabit North America after the Younger Dryas. But their culture didn't survive intact. Their sophisticated tool-making traditions didn't continue, their complex social networks didn't persist into the post-impact world. The survivors had to start over, had to develop new survival strategies for a world that had changed beyond recognition, had to abandon the specialized megafauna hunting techniques that had sustained them for generations because the megafauna no longer existed. This is what Firestone's black layer represents, what those 4 centimeters of carbon-rich sediment preserve in the geological record. Not just evidence of an impact, not merely proof that something from space struck Earth, but a marker of the moment when human civilization in North America was reset, when thriving cultures were reduced to scattered survivors, when the world our ancestors knew was destroyed and they were forced to rebuild from the ashes. And this wasn't just an American story, wasn't limited to one continent or one group of people. The global distribution of that black layer, the fact that it appears on multiple continents at the same moment, in time, suggests that the impact affected human populations worldwide. We know from archaeological evidence that complex structures were being built in other parts of the world around this time, that societies were developing agriculture, that civilization as we understand it was beginning to emerge. The site of Göbekli Tepe in Turkey, for instance, features massive stone temples dated to just after the Younger Dryas period, built by people who theoretically shouldn't have had the organization or resources to construct such monuments. Some researchers suggest these structures represent a rebuilding, a resurgence of civilization after the impact had wiped clean whatever came before. But here's where the story gets controversial, where it transitions from fascinating scientific discovery to something that makes many academics deeply uncomfortable. If a comet impact 12,800 years ago could destroy the Clovis culture, could cause mass extinctions, could plunge Earth into centuries of climate chaos, what else might it have destroyed? What other human societies might have existed before that impact, societies sophisticated enough to leave behind knowledge and traditions but unlucky enough to be wiped out so completely that only fragments of their existence survived? This is the question that keeps researchers like Firestone awake at night, the implication that lurks beneath every layer of black sediment, every nanodiamond an iridium spike. The black layer marks a boundary, a before and after in human history, a moment when something ended and something else began. Everything we know about ancient civilizations, all our carefully constructed timelines about when agriculture developed and when cities first appeared and when writing was invented, all of it assumes continuity, assumes that we can trace human, cultural development back through an unbroken chain of evidence. But what if that chain was broken 12,800 years ago? What if the Comet impact destroyed not just the Clovis culture but something older, something more sophisticated, something that left so little trace that we've dismissed the hints and rumors and legends as mere mythology? The mainstream academic response to these questions has been swift, has been dismissive, has been in some cases almost hostile in its rejection. When Firestone published his findings, when he proposed that a comet impact had triggered the Younger Dryas and caused megafauna extinctions, he expected scientific debate, expected challenges to his methodology, expected the normal back and forth that characterizes how science progresses. What he didn't expect was the vehemence of the opposition, the coordinated efforts to discredit his work, the systematic attempts to prevent follow-up research from being funded or published. Within months of the initial publication, critical papers began appearing in scientific journals, papers that questioned every aspect of Firestone's findings, that claimed the nanodiamonds were misidentified, that insisted the iridium could be explained by terrestrial processes, that argued the black layer was nothing more than normal sediment that had been misinterpreted. Some of these criticisms were valid, represented legitimate scientific skepticism, raised questions that needed to be addressed. But others seemed driven by something else, by a need to dismiss the impact hypothesis regardless of evidence, by a determination to maintain existing narratives about human history even when those narratives didn't adequately explain the data. This pattern of resistance, this wall of opposition that Firestone encountered, mirrors something we've seen before in the history of science. When evidence emerges that challenges fundamental assumptions, when discoveries threaten to rewrite textbooks and invalidate decades of accepted theory, the response from established authorities is often not curiosity but defense, not openness to new ideas but protection of old ones. The black layer in Arizona, those 4 centimeters of sediment containing nanodiamonds and iridium and evidence of global catastrophe, represents exactly this kind of challenge, this kind of threat to comfortable certainty about the past. And the resistance continues today, more than 15 years after Firestone's initial discovery. New studies keep finding more evidence of the impact, keep detecting the same markers at more sites around the world, keep building a stronger and stronger case that something extraordinary happened 12,800 years ago. Yet the dominant narrative in academic archaeology hasn't changed, hasn't incorporated these findings into the standard story of human development, hasn't acknowledged that maybe, just maybe, we need to rethink what we know about the world our ancestors inhabited and what they experienced during that catastrophic moment when the sky fell and civilization burned. The question isn't whether the black layer exists, the evidence for that is overwhelming, documented at dozens of sites, confirmed by multiple independent research teams. The question is what we're willing to accept about what that layer represents, what we're prepared to believe about human history, and how far the implications of a cosmic impact might extend beyond simple climate change and extinction events into the realm of lost civilizations, preserved knowledge, and secrets buried so deep in time that we've forgotten they were ever hidden. The Clovis people were not primitive, were not simple hunter-gatherers scratching out a bare existence in the Ice Age wilderness, were not the cavemen of popular imagination. They were sophisticated, skilled, innovative people who had developed one of the most advanced stone tool technologies the world had ever seen, who had spread across an entire continent in just a few centuries, who had created a culture so successful that their distinctive spear points appear at hundreds of sites from Alaska to Mexico. These weren't random wanderers, weren't disconnected bands barely surviving. They were a civilization, perhaps not in the way we typically use that word, not with cities and writing and agriculture, but certainly in terms of cultural complexity, technological achievement, and geographical reach. Their signature weapon, the Clovis point, represents a level of craftsmanship that still impresses modern knappers, still challenges anyone trying to replicate their techniques. These weren't crude stone tools, weren't rocks barely chipped into useful shapes. They were masterpieces of engineering, carefully designed projectile points with fluted channels running up both sides, thin bases, that allowed them to be hafted onto spear shafts with precision, edges sharp enough to penetrate the thick hide of a mammoth. Creating one required understanding stone properties at an almost intuitive level, required knowing exactly where to strike to remove flakes in the right pattern, required patience and skill developed over years of practice. And they made thousands of them, left them scattered across North America in such quantities that finding Clovis points became almost routine for archaeologists working in late Pleistocene sites. The distribution tells a story of trade networks, of cultural exchange, of people moving across vast distances and maintaining connections with distant groups. Points made from stone quarried in Wyoming appear in Texas, tools crafted from Ohio flint show up in Florida, raw materials from sources hundreds of miles apart get found together at single sites. This wasn't random, wasn't coincidence, wasn't the result of isolated bands happening to travel the same routes. This was systematic, was organized, was evidence of a culture that had figured out how to maintain connections across continental distances. The megafauna they hunted were creatures from another world, animals so large and strange that if we hadn't found their bones, if we had only ancient descriptions to go by, we'd probably dismiss them as mythology. Columbian mammoths stood 14 feet tall at the shoulder, weighed 10 tons, carried tusks that curved upward and inward in elegant spirals that could reach 16 feet in length. They weren't the woolly mammoths of Arctic regions, those shaggy cold-adapted creatures we see in illustrations. These were built for temperate climates, for the grasslands and parklands of Ice Age North America, for environments where vegetation was plentiful and herds could range across vast territories following seasonal growth patterns. Giant ground sloths, creatures that modern people would struggle to even comprehend, stood on their hind legs, at heights rivaling the mammoths, used massive claws to strip branches from trees, moved with a slow deliberateness that made them seem almost contemplative. Some species reached weights of 4 tons, masses comparable to modern elephants, bodies adapted for browsing high vegetation that other animals couldn't reach. They were strange, were unlike anything alive today, were reminders that the Pleistocene was genuinely alien compared to our modern world, populated by creatures that would seem impossible if we hadn't excavated their skeletons from ancient lakebeds and cave deposits. Saber-toothed cats prowled these environments as apex predators, carrying canine teeth that extended 8 inches beyond their gums, teeth so long they couldn't close their mouths completely, teeth designed not for typical predator biting but for a specialized killing technique. They hunted the megafauna, took down prey far larger than themselves through pack cooperation, and those devastating saber fangs drove those teeth deep into the soft tissues of necks and bellies, severed major blood vessels with surgical precision. They were built for this, had evolved over millions of years to perfect the art of killing giants, had body plans optimized for grappling with prey that weighed several times their own mass. American lions, larger than any cat alive today, ranged across the same territories, competing with saber-tooths for prey, filling a slightly different ecological niche through their ability to take down faster prey that the stockier saber-tooths couldn't catch. Dire wolves hunted in packs, coordinated attacks on megafauna calves and weakened adults, filled the social predator role that modern wolves occupy but did so at a scale appropriate to their Pleistocene prey base. Short-faced bears, the largest terrestrial mammalian carnivores in North America, stood 12 feet tall, on their hind legs, possessed long limbs that made them surprisingly fast for their size, may have been primarily scavengers but were certainly capable of driving other predators from kills through sheer intimidation. This was the world the Clovis people inhabited, the ecosystem they had learned to exploit, the environment they had mastered through a combination of technological innovation and cultural knowledge passed down through generations. They weren't just surviving in this landscape, weren't merely eking out an existence alongside these enormous animals. They were thriving, were successfully hunting creatures that other predators approached with caution, were sophisticated enough to take down mammoths regularly enough that mammoth kill sites became common features in the archaeological record. The sites themselves tell stories of successful hunts, of groups coordinating to drive mammoths into favorable terrain, of butchering techniques refined over generations. At Murray Springs in Arizona, archaeologists found a butchered mammoth skeleton with Clovis points lying among the bones, the animal still articulated, still in anatomical position, preserved exactly as the hunters had left it after processing the meat and useful materials. The skeleton was stained black, discolored by contact with the overlying sediment layer, that same black mat that Richard Firestone would later analyze for evidence of cosmic impact. Vance Haynes, the archaeologist who excavated Murray Springs, determined that the mammoth had been butchered no more than a few weeks before the black mat was deposited, perhaps as little as a few days before that mysterious layer covered the site. The timing was critical, was precise, was almost eerie in its implications. The Clovis hunters had killed this mammoth, had processed it, had likely moved on to the next hunting ground, and then, very shortly afterward, something happened that buried the entire site under that black layer of sediment. The mammoth's bones remained exactly where the hunters had left them, frozen in time, preserved by whatever catastrophic event deposited that dark layer. And here's what makes this discovery truly haunting, what transforms it from interesting archaeological site to potential crime scene of a global catastrophe. Below that black layer, Clovis artifacts are everywhere, appear consistently, represent an active presence of humans using sophisticated stone technology. Mammoth bones, fresh enough to show butcher marks, lie in context suggesting recent kills, recent processing, recent human activity. The site was alive with human presence, was a location where Clovis people were actively exploiting the environment, were successfully hunting the largest animals on the continent, were living their normal lives right up until that black layer was deposited. Above the black layer, nothing. No more Clovis points, no more megafauna bones, no more evidence of human activity for what may have been centuries. The archaeological record goes silent, stops as abruptly as if someone had flipped a switch, marks a boundary that archaeologists call the Clovis barrier. It's not subtle, isn't a gradual decline, isn't a slow transition from one culture to the next. It's a hard stop, an immediate termination, a moment when the Clovis culture ceases to exist in the material record. Vance Haynes, describing this pattern, used language that's unusually stark for academic archaeology. He wrote that the sudden extinction of Pleistocene megafauna would be dramatically revealed by explaining that all were gone an instant before the black mat was deposited. An instant, not gradually, not over generations, not through a slow process of environmental change and adaptive failure. An instant, a single moment, a line in the sediment that marks before and after with shocking precision. The same pattern repeats at site after site across North America. At Blackwater Draw in New Mexico, the Clovis-type site where this distinctive stone tool tradition was first recognized and named, the black mat separates a world with Clovis artifacts and megafauna from a world without either. Below the mat, excavators found mammoth bones, bison remains, evidence of successful Clovis hunting. Above it, for a depth representing centuries of time, there's essentially nothing, a gap in the archaeological record that suggests human populations either disappeared entirely from the region or declined so dramatically that they left no detectable trace. At the Wally's Beach site in Canada, researchers found that black layer inside the skull of an extinct horse, the sediment preserved within the cranial cavity, showing that burial happened rapidly, happened before scavengers could scatter the bones, happened while the carcass was still relatively fresh. The layer contained iridium at concentrations of 51 parts per billion, more than 10 times higher than background levels, clear evidence that whatever deposited that black mat included material from space, included the signature of an extraterrestrial impact. Across the Carolina Bays, those mysterious elliptical depressions that dot the Atlantic coastal plain, from New Jersey to Florida, the same black layer appears, dated to the same moment, containing the same mixture of carbon and impact markers. The bays themselves have long been controversial, have been proposed as impact craters from some ancient catastrophe, though mainstream geology has typically explained them as wind and wave features from earlier periods. But the presence of that 12,800-year-old black layer, the layer with nanodiamonds and iridium, the layer that marks the Younger Dryas boundary, suggests maybe the alternative explanation deserves reconsideration. The extinction pattern among megafauna shows the same abruptness, the same suddenness, the same quality of happening all at once rather than gradually. 35 genera of large mammals disappeared from North America during a window that may have been as short as a few decades, certainly no more than a few centuries. That's not evolutionary time, isn't the scale on which species normally go extinct through competition or climate change or gradual environmental shifts. That's catastrophic time, the kind of timeline associated with asteroid impacts and supervolcanic eruptions and other disasters that reset ecosystems entirely. Some of these animals had existed for millions of years, had survived multiple ice ages and warm periods, had weathered dramatic climate fluctuations without going extinct. Mammoths and mastodons had been in North America for hundreds of thousands of years, had adapted to cold periods and warm periods, had proven their resilience through countless environmental changes. Giant ground sloths had thrived for millions of years across South and North America, had diversified into multiple species occupying different ecological niches, had shown no signs of being vulnerable to extinction. Then suddenly, within what may have been a single human lifetime, they were gone. Not declining, not showing signs of stress in the years leading up to extinction, but simply gone, vanished from the fossil record as completely as the Clovis culture vanished from the archaeological record. The coincidence is too perfect, too precise, too synchronized to be unrelated. Whatever happened to cause that black layer to be deposited across North America, whatever event left nanodiamonds and iridium scattered across the continent, also killed the megafauna and ended the Clovis culture. But here's where the story gets even more disturbing, where the implications expand beyond North America, beyond a regional catastrophe, into something that affected the entire planet. The megafauna extinctions weren't limited to North America, weren't isolated to one continent or one ecosystem. South America lost most of its large mammals during the same period, saw species that had evolved in isolation for millions of years suddenly disappear. Giant ground sloths that had never encountered Clovis hunters, that lived in regions where human populations were sparse or possibly absent, went extinct on the same timeline. Glyptodonts, those bizarre armadillo-like creatures the size of small cars, disappeared from South American ecosystems where they had thrived for millions of years. Toxodon, massive hoofed mammals that looked like a bizarre cross between a rhino and a hippo, vanished despite having no natural predators capable of threatening adults. Macroeuchenia, strange camel-like creatures with short trunks, went extinct across their entire range. The list goes on, encompasses dozens of species, represents the collapse of entire ecological communities. Australia experienced its own megafauna extinction around the same period, though dating is less precise and more controversial. Giant wombats, massive kangaroos, carnivorous marsupial lions, all disappeared in what may have been a relatively short window of time. The exact chronology is debated, with some researchers placing the extinctions earlier, but the possibility remains that these events were connected, were part of a global pattern, were responses to the same catastrophic trigger that affected North America. Europe and Asia lost species too, though not as dramatically, not with the same overwhelming completeness. Woolly rhinoceros, cave bears, giant deer, all declined and eventually vanished during the late Pleistocene. Some of these extinctions happened earlier, some later, making the pattern less clear than in the Americas. But the concentration of extinctions around the Younger Dryas boundary, around that 12,800-year mark, suggests that whatever happened during that period delivered a devastating blow to megafauna populations worldwide. The question that haunted researchers, the puzzle that needed solving, was mechanism. How do you kill off dozens of species across multiple continents simultaneously? Climate change alone doesn't work, because these animals had survived previous climate changes, had proven their ability to adapt to warming and cooling cycles. Human hunting doesn't work either, because humans hadn't reached some of these regions yet, and, in places where they had, humans and megafauna had coexisted for thousands of years without causing extinctions. You need something sudden, something catastrophic, something capable of affecting entire continents simultaneously. You need something that can disrupt ecosystems at a fundamental level, that can kill animals directly through immediate effects while also creating long-term environmental changes that prevent survivors from recovering. You need, in other words, something like a comet impact, like fragments of a disintegrating comet entering the atmosphere over multiple regions, exploding in airbursts that devastate the landscape below, triggering wildfires and climate chaos and ecological collapse. The Clovis people, standing somewhere in this landscape as the sky began to glow, as the first impacts hit, as the world they knew started to burn, would have understood immediately that something unprecedented was happening. They were skilled observers, were people whose survival depended on reading environmental signs, on understanding weather patterns and animal behavior and seasonal changes. They would have recognized instantly that this wasn't normal, wasn't anything their ancestors had experienced, wasn't something their accumulated cultural knowledge could help them survive. Some must have lived through it, must have found shelter, must have endured the initial impacts and the fires and the impact winter that followed. Humans didn't go extinct, didn't disappear from North America entirely, continued to inhabit the continent after the Younger Dryas. But something changed, something fundamental, something that transformed their culture so completely that the Clovis tradition ended, disappeared, got replaced by different tool technologies, different survival strategies, different cultural patterns. The archaeological record shows a hiatus, a gap of perhaps several centuries where human presence in some regions becomes nearly invisible, where populations seem to have crashed, where the elaborate social networks that characterized Clovis culture fell apart. Vance Haynes suggested a post-Clovis hiatus of at least 500 years in human occupation at and around Murray Springs, half a millennium where the region that had supported thriving Clovis populations appears nearly empty. Other researchers found similar gaps in different regions, periods of 100 years or more where archaeological evidence becomes extremely scarce, where human populations seem to have declined to levels that left minimal material traces. This isn't what you'd expect if climate change alone ended the Clovis culture, isn't the pattern of gradual adaptation and cultural evolution. This is what you'd expect if something killed a large percentage of the population suddenly, if survivors were scattered and traumatized, if the social structures that had supported Clovis culture collapsed under the weight of catastrophe. The megafauna they had hunted were gone, had been their primary food source, had been the foundation of their subsistence strategy. Clovis technology had been optimized for taking down large animals, their social organization had been built around the logistics of hunting and processing mammoths and other megafauna. When those animals disappeared, when the ecosystem collapsed, the specialized adaptation that had made Clovis people so successful became a liability, became a skill set designed for a world that no longer existed. The survivors had to adapt, had to develop new hunting techniques for smaller prey, had to reorganize their societies around different resource bases, had to essentially start over in a world that had been devastated by fire and climate chaos. Some succeeded, developed new cultural traditions that archaeologists identify by different tool types and different site patterns. The Folsom culture, which followed Clovis after that mysterious gap in the record, hunted bison with different point styles, showed different social organizations, represented a new adaptation to a changed world. But something was lost, some continuity was broken, some accumulated knowledge from the Clovis period didn't get passed down to their successors. The sophisticated fluting technique used to make Clovis points largely disappeared, got replaced by different manufacturing methods. The continent-wide trade networks contracted, became more regional, lost the long-distance connections that had characterized Clovis culture. Whatever had happened at that moment 12,800 years ago, whatever event deposited that black layer over their kill sites and burial grounds, had done more than just kill animals and people. It had shattered a culture, had broken the transmission of knowledge from one generation to the next, had forced a reset of human society in North America. And if this happened to the Clovis people, if a sophisticated culture that had successfully spread across an entire continent could be effectively destroyed in a single catastrophic event, what might have happened to other human societies elsewhere in the world? What other cultures might have existed before that moment, might have achieved their own sophisticated adaptations to their environments, might have left only fragmentary traces because the comet impact destroyed them so thoroughly? The black layer marks a boundary, a moment when one world ended and another began, a line in the sediment that asks uncomfortable questions about what we've lost, what we've forgotten, what stories died, when the survivors were too few and too traumatized to preserve everything their ancestors had known. The ice didn't melt slowly, didn't retreat gradually over centuries as ice sheets normally do when climate warms, didn't follow the predictable patterns that glaciologists had documented from other periods of deglaciation. It collapsed, came apart catastrophically, released inconceivable quantities of water into the North Atlantic in what may have been a matter of days or weeks rather than decades or centuries. This wasn't normal climate change, wasn't the kind of gradual warming that allows ecosystems to adapt, allows species to migrate to new territories, allows ice to retreat in an orderly fashion that geologists can model and predict. This was something else entirely, something violent, something that happened so fast that the evidence still looks anomalous 12,800 years later. James Kennett, a geologist who had spent decades studying ocean sediments and climate change, was examining ice cores, drilled from the Greenland ice sheet when he noticed something that didn't make sense, something that violated everything he understood about how ice ages end. The cores preserve a record of temperature and precipitation going back hundreds of thousands of years, each annual layer of snowfall compressed into ice, each layer containing chemical signatures that reveal what conditions were like when that snow fell. Reading ice cores is like reading tree rings, except instead of years you're looking at climate data spanning geological time scales, instead of growth patterns you're measuring oxygen isotopes and dust particles and trapped air bubbles. The data from the onset of the Younger Dryas showed a temperature drop so abrupt, so dramatic, that if you plotted it on a graph it looked almost vertical, looked like someone had pushed the climate off a cliff. Temperatures in Greenland, which had been warming steadily for thousands of years as Earth emerged from the last ice age, suddenly plummeted by 15 degrees Celsius within a span that the ice core resolution suggested might be as short as 3 years. 3 years, not 300, not 3,000. 3 years to drop from conditions approaching modern climate back to full ice age temperatures, from warming trends to bitter cold that would persist for 13 centuries. That kind of change shouldn't be possible through normal climate mechanisms, through the gradual shifts in ocean currents and atmospheric circulation that drive climate on human timescales. You need something catastrophic, something that can inject enough energy into the climate system to overwhelm all the normal feedbacks and buffering mechanisms, something that can force a rapid state change from one stable climate configuration to another. Kennett knew this, understood the implications, felt the weight of what the ice cores were telling him even before he connected it to the comet impact hypothesis that Richard Firestone would propose years later. But temperature wasn't the only anomaly in those ice cores, wasn't the only signal suggesting something extraordinary had happened. The chemical composition of the ice changed at exactly that same boundary, showed spikes in elements and compounds that shouldn't be there in those concentrations, that required explanations beyond normal atmospheric processes. Ammonium levels increased dramatically, showed concentrations that researchers interpreted as evidence of massive biomass burning, of forests across vast regions going up in flames simultaneously. Not local fires, not seasonal burning that could be explained by lightning strikes or human activity, but continent-scale conflagrations that pumped enough smoke into the atmosphere to leave clear signatures in Greenland ice 1,000 miles away. Nitrate concentration spiked too, along with formate, oxalate, and acetate, all compounds associated with combustion, all markers that appeared in the ice core record when massive wildfires occurred downwind of Greenland. The researchers who first documented these spikes, who published their findings in the early 1990s before the impact hypothesis had been proposed, struggled to explain them. What could cause fires extensive enough to show up so clearly in ice cores? What could burn across such vast areas that the smoke would drift to Greenland in concentrations high enough to be detected thousands of years later? Then Paolo Gabrielli, an Italian geochemist, analyzed the same ice cores for trace metals, looking for evidence of volcanic eruptions, looking for the signatures of cosmic dust, looking for anything anomalous in the chemical record of Earth's atmosphere. What he found was platinum, iridium, and other platinum group elements at concentrations that exceeded normal background levels by factors of 10 or more. The spike occurred at exactly the Younger Dryas boundary, at exactly the same moment the temperature dropped and the biomass burning signals appeared, at exactly the depth in the ice that corresponded to 12,800 years ago. Gabrielli initially attributed the platinum spike to increased cosmic dust input, suggested that, perhaps Earth had passed through a meteor shower, had intersected with debris from a comet's orbital path. It was a conservative interpretation, one that didn't require invoking a major impact event, one that mainstream science could accept without challenging fundamental assumptions about climate history. But when Firestone's team published their findings about nanodiamonds and impact markers in the black matte layer, when the evidence began mounting for an actual comet impact rather than just cosmic dust, Gabrielli's platinum spike suddenly took on new significance, suddenly looked less like background cosmic material and more like the fingerprint of an impact. The ice cores revealed something else too, something even more disturbing when you understood its implications for how quickly climate can change, how fragile the systems that regulate global temperature really are. The layer of ice deposited during the first years of the Younger Dryas contained freshwater, showed chemical signatures, indicating it came from melted glacial ice rather than normal snowfall, suggested that massive quantities of ice had melted and been lofted into the atmosphere as vapor before condensing and falling as precipitation over Greenland. This was backwards, was the opposite of what should happen during a cooling period, was evidence that, even as temperatures were plummeting, ice somewhere was melting catastrophically. The source of that meltwater became clear when researchers examined ocean sediments from the North Atlantic, when they analyzed cores taken from the seafloor off the coast of eastern Canada and Greenland. The sediment showed a massive influx of fresh water during the onset of the Younger Dryas, showed evidence that the Laurentide ice sheet, the enormous glacier that covered most of Canada during the last ice age, had partially collapsed, had released billions of tons of meltwater into the North Atlantic in a geological instant. Not gradually, not through normal melting, but catastrophically, as if something had destabilized the ice sheet, had injected enough heat to cause massive sections to collapse and disintegrate. Imagine what this would have looked like, what it would have meant for anyone living near the ice sheets when this happened. The Laurentide ice sheet was enormous, was larger than the current Greenland ice sheet, covered an area of roughly 5 million square miles with ice up to 2 miles thick in places. It was a frozen continent, a massive reservoir of water locked up as ice, a geological feature that dominated the northern landscape of North America. When sections of it collapsed, when the ice came apart and fell into the ocean or melted in place, it would have created floods of biblical proportions, walls of water surging across the landscape, carrying icebergs, the size of buildings, scouring everything in their path. The meltwater would have been freezing, would have been barely above 0 degrees Celsius, would have flooded into the North Atlantic with enough volume to affect ocean circulation on a global scale. The Atlantic meridional overturning circulation, the system of currents that includes the Gulf Stream, depends on salinity gradients, depends on dense salty water sinking in the far North Atlantic and driving a conveyor belt of circulation that distributes heat around the globe. When billions of tons of fresh water suddenly dilute that salty water, when the density gradient collapses, the circulation shuts down, stops redistributing heat from the tropics to northern latitudes, allows the Arctic to freeze while tropical regions continue receiving the same solar energy they always do. This is what happened at the onset of the Younger Dryas. This is how a comet impact could trigger a return to Ice Age conditions, even though Earth's orbital configuration was promoting warming, even though solar radiation hadn't changed, even though all the normal drivers of climate were pushing toward deglaciation. The impact melted enough ice to shut down the Atlantic circulation, and when that circulation stopped, northern Europe and North America plunged back into deep freeze while other parts of the world experienced different climate anomalies, different responses to the disruption of normal heat distribution patterns. The evidence from Greenland itself shows this paradox in stark detail, shows the contradiction that makes the Younger Dryas so puzzling to climate scientists who don't accept the impact hypothesis. Ice cores from the Greenland ice sheet, the massive glacier that still covers most of that island, show that temperatures dropped dramatically during the Younger Dryas, show that conditions became colder than they had been for thousands of years. But the margins of that same ice sheet show evidence of retreat, show that the glacier were pulling back, were losing mass even as temperatures plummeted. Elizabeth Rainsley, a glaciologist studying this paradox, found evidence that seemed impossible, seemed to violate basic physics. She examined exposed bedrock in areas that had been covered by ice during the last glacial maximum, used cosmogenic isotope dating to determine when those rocks had been uncovered, when the ice had retreated enough to expose them to cosmic rays. The dates came back clustered around the Younger Dryas period, showed that the ice had pulled back substantially between 12,900 and 11,700 years ago. During the cold period, during the time when temperatures were supposed to be dropping and glacier should have been advancing, the Greenland ice sheet was losing mass, was retreating, was behaving as if it were warming rather than cooling. The explanation involves ocean currents, involves the same shutdown of Atlantic circulation that caused the atmospheric cooling, involves complex interactions between surface temperatures and deep ocean heat. When the Atlantic meridional overturning circulation collapsed, when the conveyor belt of warm surface water stopped flowing northward, it didn't eliminate all the heat in the ocean. It just stopped distributing it, allowed warm water to pool at depth in certain regions, created conditions where the deep ocean could be relatively warm even while surface temperatures and atmospheric temperatures were dropping dramatically. The Irminga Current, a branch of the Gulf Stream that flows along the western coast of Iceland and approaches southeastern Greenland, strengthened during the Younger Dryas even as surface circulation weakened, carried warm water at depth that melted the Greenland ice sheet from below, caused massive carving of icebergs, drove retreat of marine terminating glacier that were being undercut by warm water even as they experienced cold air temperatures. This is what Rainsley found, this is what explained the paradox of ice retreat during atmospheric cooling, this is what showed just how complex the climate system's response to disruption can be. But this raises uncomfortable questions, forces us to confront implications that extend beyond academic debates about climate mechanisms. If warm subsurface water could melt the Greenland ice sheet from below during the Younger Dryas, if glacier could retreat rapidly despite cold atmospheric temperatures, what does that mean for the modern Greenland ice sheet facing similar ocean warming today? If the climate system can flip between stable states as rapidly as the ice cores suggest, if transitions can happen on timescales of years rather than centuries, how vulnerable is our current climate to rapid changes that could overwhelm our ability to adapt? The Greenland ice sheet during the Younger Dryas lost an estimated 280 meters of thickness in the southeastern sector, lost mass at rates that seem almost incomprehensible when you calculate the volume of ice involved. 280 meters of thickness over an area covering thousands of square kilometers represents an enormous quantity of water, represents ice loss comparable to the worst-case projections for modern Greenland under future warming scenarios. Except the Younger Dryas ice loss happened over centuries, not millennia, happened despite atmospheric cooling, happened because ocean circulation had been disrupted by the catastrophic meltwater pulse that the Comet impact had triggered. The sediment cores from the ocean floor off southeastern Greenland show this meltwater pulse clearly, show a spike in freshwater indicators between 12,800 and 12,000 years ago, show evidence of massive iceberg carving and glacial retreat precisely when you'd expect glacier to be stable or advancing based on temperature records. The sediments contain ice-rafted debris, rocks and gravel that were frozen into icebergs when they carved from glacier, that were carried out to sea as the icebergs drifted, that dropped to the seafloor when the icebergs melted. The quantity of this debris increases dramatically at the Younger Dryas boundary, suggests that iceberg production increased by orders of magnitude, that the ice sheet was coming apart in massive carving events rather than retreating gradually, through melting. This pattern repeats around other sections of the Greenland ice sheet, shows up in sediment cores from different fjords and different coastal regions, demonstrates that the ice loss wasn't localized, wasn't isolated to one glacier or one region. The Jakobshavn Isbrae, one of the largest and most active glacier in western Greenland, shows evidence of major retreat during the early Younger Dryas, retreated inland by dozens of kilometers while temperatures were dropping, behaved in ways that make no sense unless you understand the subsurface ocean warming mechanism. The Kangerlussuaq Glacier in eastern Greenland shows similar retreat, similar evidence of mass loss during atmospheric cooling, similar responses to disrupted ocean circulation. And all of this traces back to that initial catastrophic meltwater pulse, to the moment when the Comet impact destabilized the Laurentide ice sheet, caused it to release enough freshwater to shut down Atlantic circulation, triggered a cascade of climate feedbacks that plunged Earth back into ice age conditions even while simultaneously melting the Greenland ice sheet from below. It's a perfect example of how complex climate systems can be, how non-linear their responses to perturbations, how a single catastrophic event can trigger multiple seemingly contradictory effects through different mechanisms operating on different timescales. The Laurentide collapse left its own geological signatures, left evidence that researchers can still detect in lake sediments and ocean cores and exposed bedrock thousands of miles from where the ice sheet once stood. Lake Agassiz, an enormous glacial lake that formed along the southern margin of the Laurentide ice sheet as it began to melt after the last glacial maximum, shows evidence of catastrophic drainage events, shows layers in sediment cores that mark moments when ice dams failed and the lake emptied in massive floods. One of these drainage events occurred at exactly the Younger Dryas boundary, shows that the lake level dropped dramatically as water found new outlets, as ice dams that had contained it suddenly failed. The timing is too precise to be coincidence, too well aligned with the Comet impact date and the onset of atmospheric cooling and the meltwater pulse in the North Atlantic. Something destabilized the ice sheet, something caused ice dams to fail and glacial lakes to drain and massive sections of the Laurentide to collapse simultaneously, and the most plausible explanation is thermal shock from comet airbursts, is heat injection from multiple impacts and atmospheric explosions occurring over and near the ice sheet. The nanodiamonds in the black matte layer appear at Laurentide margin sites, appear in sediments that were deposited right at the ice edge, suggest that impacts occurred over or very near the ice sheet itself. If comet fragments exploded in airbursts over the Laurentide ice sheet, if those explosions released the energy equivalent of hundreds of nuclear weapons over a short period, the thermal pulse would have been devastating, would have injected enormous quantities of heat into ice that was already at the pressure melting point in many places, would have triggered catastrophic melt and collapse. The shock waves from the explosions could have fractured ice dams, could have destabilized ice that was barely holding together through mechanical equilibrium, could have initiated carving cascades where the failure of one section triggered failures in adjacent sections through stress redistribution. The result would have been exactly what the geological evidence shows, exactly what the ocean sediment cores and lake records and ice sheet reconstructions all demonstrate. Massive ice collapse, catastrophic meltwater release, billions of tons of freshwater flooding into the North Atlantic over weeks or months, salinity collapse that shut down ocean circulation, atmospheric temperature drops that happened too fast for ecosystems to adapt, glacial retreat driven by subsurface warming even while surface temperatures plummeted. It all fits together, all makes sense when you accept the comet impact as the triggering mechanism, all explains paradoxes that mainstream climate science has struggled with for decades. But the ice sheet collapse had effects beyond just climate change, beyond just temperature drops and ocean circulation disruption. The meltwater had to go somewhere, had to drain into the ocean or run off into rivers and lakes, had to flood across landscapes that weren't prepared for that volume of water. The massive proglacial lakes that formed along ice sheet margins would have expanded rapidly, would have inundated lowland areas, would have drowned river valleys and coastal plains under hundreds of feet of water. When ice dams failed and lakes drained catastrophically, the floods would have been incomprehensible in scale, would have made modern flood disasters look trivial by comparison. Imagine living downstream from Lake Agassiz when an ice dam failed, when billions of gallons of backed-up glacial meltwater suddenly found an outlet and came roaring down river valleys in a wall of water hundreds of feet high. Everything in the path would be destroyed, would be scoured down to bedrock, would be buried under debris fields of ice and rock and uprooted vegetation. The floods would carry icebergs, would transport boulders the size of houses, would reshape entire landscapes in a matter of hours or days. The scablands of eastern Washington state show what these glacial outburst floods can do, show channels carved hundreds of feet deep into solid basalt, show evidence of water flows that reached volumes measured in millions of cubic feet per second. The Younger Dryas floods were larger, were more catastrophic, were triggered not by gradual ice sheet retreat but by sudden impact-induced collapse. The evidence appears in sediment sequences across North America, appears in layers of chaotic deposits that mark moments of catastrophic flooding, appears in erosional features that can only be explained by water flows far exceeding anything modern rivers could produce. These flood deposits appear at the Younger Dryas boundary, appear at the same stratigraphic position as the black mat with its nanodiamonds and iridium, appear in contexts that link them directly to the comet impact and its cascading consequences. For humans living through this, for any Clovis people who survived the initial impacts and fires and shock waves, the floods would have been another catastrophe in a sequence of catastrophes, another disaster, in a world that had already ended once and was now ending again through different mechanisms. The hunting grounds they knew would have been transformed, would have been buried under water or scoured by floods, would have become unrecognizable landscapes where familiar landmarks had disappeared and familiar resources were no longer accessible. The megafauna they hunted would have been displaced or killed, would have drowned in floods or starved in transformed ecosystems, would have gone extinct not just from the immediate effects of impact but from the cascading environmental changes that followed. The climate chaos would persist for centuries, would last the entire 1300-year duration of the Younger Dryas, would create conditions that made recovery nearly impossible for human populations that had been devastated by the initial catastrophe. Cold temperatures would limit plant growth, would restrict the areas where humans could survive, would force adaptation to resources and environments very different from what pre-impact populations had known. The specialized megafauna hunting skills that had made Clovis culture successful would become useless, would be knowledge that couldn't be applied in a world without mammoths and giant ground sloths and the other enormous animals that had sustained their ancestors. This is what the ice cores reveal, this is what the ocean sediment records demonstrate, this is what the geological evidence for catastrophic ice sheet collapse tells us about the Younger Dryas and the Comet impact that triggered it. Not just a simple cooling event, not just a minor climate hiccup in the long progression of ice, ages, and interglacials, but a genuine catastrophe, a moment when Earth's climate system was knocked out of one stable state and forced into another through violent external forcing, a boundary in time when the world changed so dramatically and so quickly that recovery took over a millennium and the civilizations that existed before the impact never fully reconstituted themselves afterward. The nanodiamonds weren't supposed to exist, shouldn't be found in surface sediments, shouldn't appear in contexts that have nothing to do with volcanic activity or deep geological processes. Diamonds form under extreme conditions, require pressures that exceed 100,000 atmospheres, need temperatures above 2,000 degrees Celsius, demand environments found deep in Earth's mantle or at impact sites where cosmic objects slam into the planet at hypervelocity. Finding them in a thin layer of sediment dated to 12,800 years ago, scattered across multiple continents, appearing at dozens of sites with no geological connection to each other, should have been impossible, should have raised questions that demanded answers rather than dismissal. Yet when Firestone's team reported nanodiamonds in the Younger Dryas boundary layer, when they published electron microscope images showing these crystalline structures embedded in the black mat sediments, when they provided detailed chemical analyses confirming these were indeed diamonds rather than some other carbon structure, the response from many mainstream scientists wasn't curiosity but hostility, wasn't interest but immediate rejection, wasn't scientific debate but something that looked uncomfortably like defensive denial. The nanodiamonds became a battleground, became the focal point of efforts to discredit the impact hypothesis, became ammunition in what transformed from scientific discourse into something more resembling tribal warfare. Critics claimed the nanodiamonds were contamination, were artifacts of sample preparation, were misidentified carbon structures that weren't actually diamonds at all. They published papers arguing that the laboratory techniques used to isolate and identify the nanodiamonds were flawed, that the chemicals used in processing could have created diamond-like structures artificially, that researchers were seeing what they wanted to see rather than what was actually there. These criticisms had some initial credibility, raised legitimate methodological questions, forced proponents to refine their techniques and provide more rigorous evidence. But then independent research teams, working in different laboratories with different protocols, using different analytical methods, started finding the same nanodiamonds at the same stratigraphic positions. James Kennett, the geologist who had been studying ice cores and ocean sediments, found them in sites across California. Douglas Kennett, an archaeologist working at different locations, detected them in the Channel Islands and along the Pacific coast. European researchers found them in Belgium and the Netherlands, Asian teams discovered them in Syria, South American scientists located them in Chile. The nanodiamonds appeared everywhere. Researchers looked at that 12,800-year boundary, appeared consistently enough that dismissing them as contamination or procedural artifacts became increasingly difficult to justify. The diamonds came in different types, showed different structures that all required the same extreme formation conditions. Some were cubic diamonds, the standard crystal structure familiar from gemstones, just nanoscale in size. Others were hexagonal diamonds, also called lonsdaleite, a form that only appears in meteorites and at impact sites where shock pressures transform normal cubic diamonds into this alternative crystal structure. Finding both types together, finding them in the same sediment layer, finding them associated with other impact markers, created a signature that was hard to explain through any mechanism except extraterrestrial impact. Then there were the carbon spherules, tiny balls of carbon that looked like frozen droplets, that showed surface features suggesting they had been molten, that contained internal structures indicating rapid cooling from liquid state. These weren't charcoal fragments, weren't pieces of burned wood or vegetation, weren't normal products of wildfires no matter how intense. They were quench-melted carbon, droplets that had been heated to temperatures above 2000 degrees Celsius, hot enough to turn solid carbon into liquid, hot enough that they could only form in impact fireballs or, perhaps, in the most extreme volcanic eruptions. But there were no volcanoes in most of the locations where these spherules appeared, no evidence of eruptive activity that could explain their presence, no plausible source except the atmosphere itself, except explosions in the sky that created temperatures high enough to melt carbon and spray it across continents as microscopic droplets. The iridium spike that appeared in the same layer added another piece to the puzzle, provided another marker that pointed away from terrestrial explanations and toward space. Iridium is an element that barely exists in Earth's crust, appears in concentrations measured in parts per trillion in most rocks and sediments, stays locked in Earth's core where it sank during planetary formation billions of years ago. But it's common in asteroids and comets, appears in meteorites at concentrations thousands of times higher than terrestrial rocks, serves as a fingerprint for extraterrestrial material because there's no other reasonable way to get significant iridium enrichments in surface sediments. The Younger Dryas boundary layer showed iridium spikes at multiple sites, showed concentrations that exceeded background levels by factors of 10 or 20 or more, showed patterns that matched what you'd expect from impact debris settling out of the atmosphere. Critics tried to explain this away through volcanic activity, through processes that could concentrate iridium from normal crustal abundances, through cosmic dust accumulation over long periods. But none of these alternatives fit the data, none could explain the specific timing of the spike at exactly the Younger Dryas boundary, none could account for the global distribution pattern or the association with nanodiamonds and carbon spherules and all the other impact markers. Platinum group elements showed similar spikes, similar enrichments that appeared at the same boundary layer, that required similar explanations involving extraterrestrial sources. Platinum, osmium, palladium, all appeared in elevated concentrations in that thin black layer, all showed patterns consistent with impact debris, all added to the accumulating evidence that something from space had delivered exotic materials to Earth's surface at precisely the moment the climate changed and megafauna went extinct and Clovis culture disappeared. The platinum spike was particularly dramatic in ice cores from Greenland, where Paolo Gabrielli had documented concentrations reaching 21 times background levels right at the Younger Dryas onset. Then came the melt glass, the shocked quartz, the impact spherules that looked exactly like materials found at confirmed impact sites, that showed characteristics impossible to explain through any process except hypervelocity collision. Melt glass forms when rock is heated so intensely that it liquefies, when temperatures reach thousands of degrees, and maintain them long enough for minerals to break down completely, when the molten rock then cools quickly, enough to freeze into glassy rather than crystalline structure. You find melt glass at nuclear test sites, at volcanic craters where magma directly interacts with surface rocks, and at impact sites where the energy of collision turns solid rock into superheated liquid in microseconds. The Younger Dryas boundary layer contained melt glass at multiple locations, contained glassy particles, with compositions matching local bedrock, contained evidence that surface materials had been melted and dispersed across the landscape. The glass showed vesicles, contained gas bubbles that formed when trapped volatiles expanded in the molten rock, showed flow textures indicating it had been liquid before solidifying, showed all the features you'd expect from impact melt. Critics argued that some of this glass could be volcanic, could be from eruptions that happened to coincide with the Younger Dryas, could be explained without invoking impacts. But the volcanic explanation failed when researchers found melt glass at sites thousands of miles from any volcanic activity, found it in contexts where no eruptions had occurred for millions of years, found it associated with all the other impact markers in that same thin stratigraphic layer. Shocked quartz provided even more definitive evidence, showed features that could only form under pressures exceeding 5 gigapascals, showed microscopic deformation structures called planar deformation features that serve as diagnostic indicators of shock metamorphism. These features appear when quartz crystals are subjected to pressure waves traveling faster than the speed of sound through rock, when shock fronts compress the crystal structure so rapidly that atomic planes shift and create parallel fractures at specific crystallographic orientations. Natural geological processes like earthquakes and volcanic eruptions don't generate sufficient pressures to create these features, can't produce the shock intensities required, can't explain planar deformation features except in the context of meteorite impacts or nuclear explosions. The discovery of shocked quartz at the Younger Dryas boundary came later in the investigation, emerged as researchers specifically looked for this smoking gun evidence of impact, as they applied techniques refined at sites like Meteor Crater in Arizona and the Chicxulub Crater in Mexico. When they found it, when they documented planar deformation features in quartz grains from multiple Younger Dryas sites, when they showed that these features matched those found at confirmed impact craters, it should have settled the debate, should have convinced skeptics that an impact had occurred, should have moved the discussion from whether an impact happened to how large it was and exactly what its effects were. But the debate didn't end, the skepticism didn't evaporate, the resistance to the impact hypothesis actually intensified as evidence accumulated. This response wasn't normal scientific disagreement, wasn't the healthy skepticism that drives science forward, wasn't the legitimate questioning of new hypotheses that haven't been fully tested. This was something else, something that looked like willful denial, something that suggested certain researchers and institutions had decided the impact hypothesis couldn't be true regardless of evidence, had committed to opposing it as a matter of principle rather than as a response to data. The reasons for this opposition became clearer when you understood what was at stake, what accepting the impact hypothesis would mean for established theories and academic careers and institutional authority. The Younger Dryas had been explained for decades through purely terrestrial mechanisms, through meltwater pulses and ocean circulation changes and gradual climate feedbacks. Entire research programs had been built on studying these mechanisms, hundreds of papers had been published exploring the details, careers had been made by scientists who became experts in this established narrative. If the impact hypothesis was correct, if a comet had triggered the Younger Dryas through catastrophic effects that overwhelmed normal climate processes, then much of this work became less relevant, became detailed examination of secondary effects rather than primary causes, became refinement of mechanisms that were triggered by the impact rather than explanations for the event itself. Graduate students had written dissertations about Younger Dryas climate mechanisms, had spent years analyzing sediment cores and ice cores and pollen records, had built their expertise on understanding the conventional explanation. Professors had secured tenure by publishing research that fit within the established framework, had received grants based on proposals that assumed the standard story was correct, had taught courses presenting the Younger Dryas as a natural climate fluctuation with no extraordinary cause. If the impact hypothesis gained acceptance, if it became the new consensus explanation, then expertise in the old framework became less valuable. Then researchers who had invested careers in the conventional model would find themselves needing to catch up to a new paradigm they had actively opposed. This explains much of the hostility, explains why criticism of the impact hypothesis often seemed disproportionate to to the actual weaknesses in the evidence, explains why some researchers appeared to be arguing from conclusion rather than following where data led. It wasn't just scientific skepticism, wasn't just careful evaluation of new claims, wasn't just the normal conservative tendency of science to resist revolutionary ideas until evidence becomes overwhelming. It was defense of intellectual territory, was protection of established positions, was resistance to change that came from professional self-interest as much as from scientific principle. The pattern of criticism revealed this bias clearly, showed methods that didn't match the standards applied to conventional research. When Firestone reported nanodiamonds and critics claimed they couldn't replicate the findings, the critics' negative results were immediately accepted as definitive, while Firestone's positive results and those of other independent groups were dismissed as flawed. This violated basic scientific norms, violated the principle that positive results generally outweigh negative results when multiple independent teams report positive findings using appropriate methods. You can't replicate nanodiamonds if you don't use proper isolation and identification techniques, if you don't look in the right stratigraphic position, if you don't analyze enough samples to detect features that aren't uniformly distributed. When multiple groups reported finding the same markers using refined techniques, when they addressed the methodological criticisms and still found evidence of impact, when they published in peer-reviewed journals showing their data and explaining their methods, the critics simply moved the goalposts, claimed the evidence wasn't sufficient even when it matched or exceeded evidence accepted at other impact sites, argued that the Younger Dryas case needed higher standards of proof than confirmed impacts received. This double standard was telling, revealed that evaluation wasn't being conducted on purely scientific grounds, suggested that some researchers had decided what answer they preferred and were constructing arguments to support that preference rather than objectively weighing evidence. The debate over reproducibility became particularly contentious, became an example of how scientific discourse can be manipulated through selective emphasis and misrepresentation. Critics highlighted early failures to replicate some findings, emphasized cases where researchers couldn't detect impact markers, created an impression that the hypothesis rested on unreproducible results. But they ignored or downplayed the numerous successful replications that had accumulated by multiple research groups, dismissed positive findings as still uncertain while treating negative results as definitive, created a narrative of failed replication that didn't match the actual state of the evidence. James Lawrence Powell, a geologist who had spent his career studying impact evidence, became concerned about what he saw as premature rejection of the Younger Dryas impact hypothesis, worried that legitimate scientific evidence was being dismissed through processes that didn't reflect how science should work. He conducted a systematic review of the replication literature, examined all published attempts to detect impact markers at the Younger Dryas boundary, evaluated which studies used appropriate methods and which had methodological flaws that could explain negative results. His conclusion, published in 2022, was stark, was damning in its implications for how the scientific community had handled this hypothesis. Powell found that 39 independent research groups had reported evidence supporting the impact hypothesis, had published findings of nanodiamonds or platinum spikes or melt glass or other markers at Younger Dryas sites. These weren't papers by the original proponents repeating their own work, weren't studies by scientists already committed to the impact hypothesis, weren't research from fringe journals or questionable sources. These were mainstream scientists publishing in mainstream journals, using standard techniques, finding evidence that supported impact. The geographic distribution spanned 4 continents, encompassed over 100 individual sites, represented thousands of analyses conducted in dozens of different laboratories. Against this evidence stood a small number of critical papers, perhaps a dozen studies that claimed inability to replicate impact markers, that argued against the hypothesis, that received disproportionate attention from the scientific community and media. Powell examined these critical papers carefully, evaluated their methodologies, assessed whether their negative results actually contradicted the positive findings. What he discovered was troubling, revealed that many of the critical papers had methodological problems that explained their negative results, that some hadn't actually looked in the right stratigraphic position, that others had used techniques inadequate to detect the markers they were supposedly searching for. One frequently cited critical paper claimed to have searched for nanodiamonds at Younger Dryas sites and found none, claimed this failure proved the original findings were spurious. But Powell's review revealed that this study had used inappropriate processing methods, had looked at the wrong particle size fractions, had essentially guaranteed they wouldn't find nanodiamonds even if they were present. Another critical paper claimed iridium spikes didn't exist at most sites, but had only analyzed samples from a few locations and had used detection limits too high to identify the subtle enrichments that other researchers had documented. These flaws should have discredited the critical papers, should have led the scientific community to weight them less heavily than the positive findings from multiple independent groups using appropriate methods. Instead, the critical papers were embraced, were cited repeatedly as evidence against the impact hypothesis, were used to create an impression of failed replication that influenced how other scientists and funding agencies viewed the research. This response reflected something Powell called premature rejection, reflected a pattern where the scientific community decides a hypothesis is wrong based on inadequate evidence, based on flawed critical studies, based on social and professional factors rather than objective evaluation of data. He compared it to the rejection of continental drift in the early 20th century, to the dismissal of meteorite impact cratering as a significant geological process, to other cases where scientific consensus was simply wrong and took decades to correct despite clear evidence. The Younger Dryas Impact hypothesis, Powell argued, was following the same trajectory, was being rejected prematurely despite accumulating evidence, was being suppressed through mechanisms that had more to do with protecting established views than with legitimate scientific skepticism. The implications were troubling, suggested that modern science, despite all its sophisticated methods and peer review processes and claims of objectivity, could still fall prey to the same biases and defensive reactions that had characterized earlier eras, could still prioritize consensus over evidence when consensus felt more comfortable than revolutionary change. The crater didn't exist, couldn't be found despite extensive searches, remained conspicuously absent from a landscape that should have borne a massive scar if a comet had slammed into North America with enough force to trigger global catastrophe. Critics seized on this absence, weaponized it, treated the missing crater as definitive proof that no impact had occurred, that the entire hypothesis was fantasy built on misinterpreted evidence and wishful thinking. They asked the question repeatedly, asked it in papers and at conferences and in media interviews, asked it as if the answer settled everything: where's the crater? If a comet hit Earth 12,800 years ago, if it delivered enough energy to melt rock and create nanodiamonds and trigger climate collapse, then where's the hole in the ground? Where's the circular depression that should be visible from space? Where's the geological structure that defines every other major impact in Earth's history? The question seemed reasonable on the surface, seemed to demand an answer that impact proponents couldn't provide, seemed to expose a fundamental weakness in the hypothesis that couldn't be explained away. Impact craters are obvious features, are among the most recognizable geological structures on Earth, are so distinctive that amateur satellite image analysts can identify them from orbit. Meteor crater in Arizona spans more than a kilometer, preserves a rim elevated above the surrounding desert floor, contains impact melt and shocked rock that leave no doubt about its origin. Chicxulub in Mexico, the crater from the dinosaur-killing impact 65 million years ago, is buried under sediment but still detectable through gravitational anomalies and drilled cores, still leaves an unmistakable signature of a 20-kilometer object that vaporized on collision. If the Younger Dryas comet had been a single solid object, if it had hit the ground as an intact mass, then yes, the crater would exist, would be findable, would settle the debate immediately. But that's not what happened, wasn't how the impact occurred, wasn't the mechanism that researchers were proposing. The comet fragmented, came apart as it entered the atmosphere, broke into dozens or hundreds or thousands of pieces that spread across thousands of kilometers, that exploded in airbursts before reaching the ground, that delivered their energy to the atmosphere and surface through a completely different mechanism than a single massive crater-forming impact. This wasn't speculation, wasn't an ad hoc explanation invented to save a failing hypothesis, wasn't a convenient excuse for missing evidence. This was based on physics, on understanding how comets behave when they encounter planetary atmospheres, at cosmic velocities, on observations of actual comet fragmentations that astronomers had documented in real time. Comets aren't solid rocks, aren't dense iron-nickel asteroids that can survive atmospheric entry intact. Their aggregates are loosely bound collections of ice and dust and rocky material held together by weak gravity, are what scientists call rubble piles that have internal structures more like gravel than monolithic stone. When these fragile objects hit atmosphere at 50 or 60,000 kilometers per hour, when they encounter air resistance that generates pressures exceeding their internal strength, they come apart, fragment into pieces that continue traveling along similar trajectories but now separated from each other, now independent objects following slightly different paths. This fragmentation process is well documented, was observed directly with Comet Shoemaker-Levy 9 when it broke into more than 20 fragments before impacting Jupiter in 1994, was seen again with various meteor events captured on video showing objects breaking apart during atmospheric entry. The Tunguska event of 1908 provided the perfect analog, demonstrated exactly what happens when a relatively small cosmic object explodes in an airburst without creating a crater. Something entered the atmosphere over Siberia on June 30th. Something estimated at 50 to 60 meters in diameter, something moving at speeds that generated enormous atmospheric friction. It exploded at an altitude of 5 to 10 kilometers, released energy equivalent to 10 to 15 megatons of TNT, created a shock wave that flattened trees across 2,000 square kilometers, knocked people off their feet 100 kilometers away, created seismic waves detected as far away as Western Europe. But it left no crater, created no hole in the ground, left no obvious impact scar that would allow you to identify the site from space or from ground observation of geological features. If you didn't know where Tunguska happened, if you only had the testimony of witnesses describing explosions in the sky and forests knocked flat, if you only had evidence of widespread tree damage and no crater, skeptics might claim no impact occurred at all, might argue the evidence could be explained through other mechanisms, might demand a crater as proof. Yet we know Tunguska happened, know it was real, know it demonstrates that airburst impacts can deliver catastrophic energy without leaving craters. Scale this up, multiply it by factors of hundreds or thousands, imagine not one Tunguska-scale object but dozens or hundreds spread across thousands of kilometers, and you begin to understand what the Younger Dryas Impact might have looked like. A comet nucleus perhaps 100 kilometers in diameter approaching Earth, beginning to fragment as it enters the outer atmosphere, breaking into progressively smaller pieces as atmospheric pressure increases, creating a swarm of objects ranging from kilometers down to meters in size, all spreading across a broad path, all delivering energy through airbursts that occur at different altitudes depending on the size and composition of each fragment. The energy release would be staggering, would dwarf anything in human experience, would represent explosive force measured in thousands of megatons distributed across an area spanning much of a continent. Each airburst would create its own shock wave, its own thermal pulse, its own effects on the ground below, and collectively they would simulate nuclear war, would generate conditions similar to the nuclear winter scenarios that Cold War strategists worried about, would inject enough heat and debris into the atmosphere to trigger exactly the kind of climate disruption that the geological record shows. Christopher Moore, an archaeologist who had worked extensively on Younger Dryas sites, found himself defending the impact hypothesis against crater-focused criticism repeatedly, found himself explaining why absence of a crater didn't invalidate the evidence, found himself pointing to Tunguska as proof that airbursts don't require craters. His computer simulations, conducted with colleagues at the University of South Carolina, showed how a fragmenting comet could deliver impact signatures across multiple sites without creating any single massive crater, showed how the distribution of nanodiamonds and melt glass and other markers matched what you'd expect from a swarm of airbursts rather than one ground impact. The simulations revealed patterns that matched the archaeological data with disturbing precision, predicted exactly the kind of scattered evidence that researchers were finding, explained why impact markers appeared at dozens of sites rather than concentrated at one location. Each airburst would create a zone of extreme effects directly below it, would generate nanodiamonds from shocked carbon in the air and on the ground, would melt surface materials into glass, would start fires that could spread across vast areas depending on wind and fuel availability. The overlapping effects from multiple airbursts would create a patchwork of impact evidence, exactly what the site distribution showed, exactly what made sense if you understood the fragmentation model. But the airburst mechanism created different problems for researchers trying to prove the hypothesis, created challenges that crater-forming impacts don't face, made detection and verification more difficult in ways that critics exploited. Crater impacts concentrate evidence, create unmistakable structures that can be studied for centuries after formation, leave geological markers that are easy to identify and hard to misinterpret. Airbursts scatter evidence, spread it across wide areas where it mixes with normal sediments, create signatures that can be subtle and require careful analysis to distinguish from background materials. This explains why some early studies failed to find impact markers, why researchers who went looking at Younger Dryas sites sometimes came back empty-handed, why replication proved challenging in the first years after the hypothesis was proposed. You had to know exactly where to look, had to sample the right depth, had to use appropriate analytical techniques, had to process enough material to detect markers that weren't uniformly distributed. Finding nothing at one site didn't prove nothing existed, didn't invalidate positive results from other sites, didn't demonstrate the hypothesis was wrong unless you'd done everything correctly and still found nothing. The critics who claimed they couldn't replicate impact markers often hadn't done everything correctly, hadn't looked in precisely the right stratigraphic position, hadn't used methods sensitive enough to detect subtle enrichments, hadn't analyzed sufficient sample volumes. When other researchers went to the same sites using refined techniques, using better stratigraphic control, using more sensitive analytical methods, they often found exactly what earlier studies had missed. This pattern of failed replication followed by successful replication should have tempered criticism, should have suggested that methodological issues rather than absence of markers explained negative results, should have led to more careful evaluation of what different studies actually showed. Instead, the early negative results were promoted disproportionately, were cited repeatedly as definitive evidence against the hypothesis, were used to create a narrative of failed replication that influenced how the scientific community viewed subsequent research. Even when positive replications accumulated, even when multiple independent groups reported finding impact markers at numerous sites, the narrative of controversy persisted, the impression that the hypothesis remained unproven continued to dominate, the skepticism seemed immune to evidence that should have resolved debate. The airburst model also explained the thermal signatures, explained how fires could have been widespread enough to create the carbon layer and the combustion aerosols and the biomass burning signals that appeared in ice cores and sediment records. Each airburst would generate a thermal pulse, would create a fireball that radiated intense heat in all directions, would ignite vegetation below if conditions were dry enough and if the burst occurred low enough that heat reached the surface before dissipating. The shock waves from explosions would knock down forests, would create vast areas of fallen trees that could fuel subsequent fires, would turn standing forest into kindling waiting for ignition. The combination of thermal effects and down timber would create conditions perfect for massive firestorms, for fires that spread across entire regions, for conflagrations that pumped enormous quantities of smoke and ash into the atmosphere. These wouldn't be normal forest fires, wouldn't be the kind of wildfires that occur naturally and that ecosystems have adapted to over millions of years. These would be continent-scale burning events, would consume biomass across thousands of square kilometers simultaneously, would create smoke plumes that reached the stratosphere and circled the globe, would inject enough particulate matter into the upper atmosphere to affect climate for years. The ice core evidence supported this interpretation, showed exactly what you'd expect from massive biomass burning occurring at the Younger Dryas boundary. Ammonium concentrations spiked dramatically, showed levels consistent with forest fires burning across areas measured in millions of square kilometers. Formate and acetate increased, showed chemical signatures of combustion occurring on scales that exceeded anything in the previous 10,000 years of ice core record. Charcoal particles appeared in abundance, showed that smoke from fires reached Greenland in quantities sufficient to deposit visible evidence in annual ice layers. Some critics argued these fire signatures could be explained through normal processes, through seasonal burning or through climate-driven changes in fire frequency, through mechanisms that didn't require invoking a comet impact. But the timing was too precise, too well aligned with all the other impact markers, too synchronized across different records to be coincidental. Fire activity didn't increase gradually over decades or centuries, didn't show the kind of pattern you'd expect from climate-driven changes. It spiked suddenly, appeared as a sharp peak in the records, occurred at exactly the moment that nanodiamonds appeared and platinum spiked and temperatures began to drop, occurred at the Younger Dryas boundary, with precision that demanded explanation through a single triggering event rather than through coincidental alignment of multiple unrelated processes. The airburst effects wouldn't be limited to North America, wouldn't stop at continental boundaries, wouldn't respect geographical divisions that seem important to humans but mean nothing to physics. A fragmenting comet entering Earth's atmosphere at cosmic velocity would spread debris across whatever hemisphere it approached, would affect whatever regions happened to be facing the impact trajectory, would deliver effects to multiple continents if the entry angle and fragmentation pattern distributed pieces across sufficient geographical range. The evidence suggested exactly this kind of wide distribution, showed impact markers appearing in North America and Europe and Asia, showed platinum spikes and nanodiamonds and melt glass at sites spanning from California to Syria to Belgium. This geographical spread made sense for airburst distribution, matched what you'd predict from comet fragmentation, explained why the impact signatures appeared scattered across such vast areas rather than concentrated at one location. Each fragment would follow a slightly different trajectory, would explode at a different location, would create its own zone of effects that overlapped with zones from other fragments to create the complex pattern of evidence that archaeologists and geologists were detecting. The largest fragments might affect areas hundreds of kilometers in diameter, the smaller pieces might only impact tens of kilometers, but collectively they would cover regions measured in thousands of kilometers, would span continents, would affect the entire hemisphere. The shock waves from these explosions would travel through the atmosphere as pressure fronts, would ripple outward from impact points at supersonic velocities, would carry energy far beyond the immediate blast zones. These pressure waves would compress the air ahead of them, would heat it through adiabatic compression, would create moving walls of superheated air that could ignite fires even at distances where direct thermal radiation had dissipated. The waves would also travel through the ground as seismic shocks, would shake the earth over vast regions, would trigger earthquakes along existing faults, would destabilize slopes and cause landslides in mountainous terrain. For anyone experiencing this, for any humans who witnessed the event from locations where they could survive it, the world would seem to be ending, would appear to be experiencing apocalypse, would manifest destruction beyond anything their cultural experience had prepared them to understand. The sky would light up with multiple fireballs, would show explosions occurring in sequence across the horizon, would display phenomena that would seem supernatural, divine, utterly beyond natural explanation. The ground would shake, would tremble as if the earth itself were coming apart, would create sensations that no earthquake could match because this wasn't tectonic stress release but direct impact of shock waves from atmospheric explosions. The temperature would spike suddenly, would jump by dozens of degrees in seconds as thermal pulses arrived, would create conditions where exposed skin would burn, where clothing would ignite, where wooden structures would catch fire spontaneously. Then the shock waves would arrive, would slam into anything standing with force measured in tons per square meter, would flatten trees and structures, and anything not anchored solidly to bedrock would throw people through the air like leaves in a hurricane. The sound would be overwhelming, would exceed any thunder or explosion humans had experienced, would create pressure waves that damaged eardrums and internal organs, would continue for minutes or hours as different fragments exploded in sequence across the affected regions. Surviving this would require extraordinary luck, would depend on being in the right place at the right time, would favor people who happened to be in caves or valleys or other sheltered locations when the airbursts occurred. Being in the open, being in exposed locations, being anywhere with a clear view of the sky would be fatal, would expose you to thermal radiation and shock waves and debris that would kill through multiple mechanisms simultaneously. The only survivors would be those protected by geography, by accident of location, by circumstances that placed barriers between them and the direct effects of the explosions. And even survival of the immediate impact wouldn't guarantee long-term survival, wouldn't protect against the subsequent environmental collapse, wouldn't preserve your culture or your knowledge or your way of life against the cascading disasters that followed. The fires would spread, would consume forests and grasslands across entire regions, would destroy the ecosystems that had sustained human populations for thousands of years. The smoke would block sunlight, would create twilight conditions that lasted for months or years, would prevent plant growth and cause temperatures to drop even before the long-term climate effects kicked in. The shock to the climate system would trigger the meltwater pulses, would destabilize ice sheets, would shut down ocean circulation, would plunge the hemisphere into conditions approaching full glacial cold despite the warming trend that had been underway for thousands of years. This was the airburst mechanism, this was how a comet impact could reset civilization without leaving a crater, this was the explanation that made sense of all the scattered evidence and explained why critics who demanded craters were asking the wrong question. The crater wasn't missing, wasn't evidence against impact, wasn't a weakness in the hypothesis. The crater didn't exist because the mechanism didn't create craters, didn't involve ground impact, didn't follow the model that critics had fixed in their minds as the only valid form of cosmic catastrophe. Understanding the airburst model, accepting that impacts could occur through fragmentation and atmospheric explosion rather than through monolithic crater formation, required flexibility of thinking that some researchers seemed unable or unwilling to muster, required setting aside assumptions about what impacts should look like and accepting what the evidence actually showed. The moment the first paper appeared, the battle lines were drawn. Firestone et al. Published their bombshell in 2007, dropped it into the quiet pool of paleoclimate research like a boulder-shattering glass. Most scientific revolutions take time. This one ignited instantly. The first critics barely waited for the ink to dry before launching counterattacks. The impact hypothesis, within weeks, became a storm. Some called it the boldest new theory in climate science since Alvarez's asteroid killed the dinosaurs. Others dismissed it as pseudoscience, as wild conjecture dressed in technical language, as dangerous company for real research. Debates erupted in conference halls, in academic journals, over email lists, in the offices of funding agencies. The language sharpened. The lines between professional skepticism and professional hostility blurred. Scientists are trained to separate ideas from personal identity, but it never holds as well in practice as it does in principle. The Younger Dryas Impact split the field, not evenly, but with enough force to make careers tremble and reputations burn. Detractors pointed to what they saw as a lack of replication. They asked, again and again, where is the crater? How can an event so catastrophic, so global, so civilization-shaking, leave no single, undeniable geological signature? They said the evidence was cherry-picked, the methods hasty, the geochemical markers ambiguous, the conclusions overreaching. The most vocal skeptics asked if proponents were selling stories rather than science. Some compared the hypothesis to cold fusion. Others claimed it was as backward as creationism, a theory loved by cranks and conspiracy theorists. But the critics, too, were fighting for more than just truth. The stakes were existential. Climate science had spent decades building gradualist models, carefully tracing how meltwater pulses could shut down the Atlantic conveyor, how changes in albedo could pace the glacial cycles, how humans and climate combined to end the Pleistocene giants. Hundreds of theses, thousands of papers, millions of research dollars, all built on an understanding that great changes come slow, come through cumulative, not catastrophic, forces. A cosmic explosion resetting the world in a season, in a day, threatened not just their conclusions, but their worldview, their intellectual legacy. The rebuttals came fast and, sometimes, vicious. An influential review published just 4 years after the Firestone paper announced that the Yard impact hypothesis provides a cautionary tale for researchers, the scientific community, the press, and the broader public, warning that almost none of the original lines of evidence have been subsequently corroborated by independent tests. The review catalogued errors, irreproducible results, misidentified crystals, flawed assumptions, and illogical leaps. It declared 7 of the 12 signatures non-reproducible, the rest better explained by mundane, earthly causes. The authors called out logical fallacies, misleading information, unsupported claims, and argued that the whole hypothesis was constantly shifting, self-contradictory, and sometimes outright impossible under the laws of physics. For those who believed the event was real, it all felt like history repeating itself. Continental drift, meteorite craters, extinction by cosmic impact each had faced reasoned rebuttal, then ridicule, then delayed acceptance as evidence became overwhelming. The crater problem itself was a replay. For decades, geologists claimed all craters on Earth were volcanic. Even after nuclear test explosions proved what real impact structures looked like, skeptics insisted none could be found on land until Eugene Shoemaker and colleagues started mapping them across the globe. Evidence, meanwhile, kept piling up. Archaeologists like Chris Moore dug into buried strata at YDH sites. Soil layers told stories that agreed with Firestone's layer after layer across 4 continents. The black carbon matte, nanodiamonds, and platinum group elements told the same tale with minor variations at sites in North America, Europe, the Middle East, South America. Replications mounted. Skeptics sharpened their critiques, but the evidence did not go away. Some journals started refusing papers outright, citing lack of novelty or insufficient interest. Science moved into a kind of trench warfare. Positive findings were published in new journals, open access outlets, online portals, sometimes outside the highest prestige venues. Conferences set aside special sessions for the controversy, and those sessions quickly became standing room only, attracting not just impact researchers but anthropologists, environmental scientists, geochemists, and the occasional skeptical journalist. The room would divide, one side nodding at the evidence maps, the other scribbling criticisms, both sides knowing that careers could hinge on which camp ultimately proved right. Funding became a new battleground. Grant reviewers, wary of the media attention, started marking impact hypothesis proposals as too high risk. Some labs lost staff when grants fell through. A few junior scientists who backed the idea found themselves blacklisted from collaborative fieldwork. Grant agencies demanded extraordinary levels of proof. Those already established, like Firestone and Comet, survived mainly because they had tenure, but younger researchers could not afford the risk. It turned into a war of persistence. Proponents kept hunting for new evidence, refining methods, publishing results, defending the claim point by point. They hammered, again and again, on the global pattern of geochemical markers, on the synchrony of climate change, extinction, and cultural collapse. Skeptics pressed their advantage each time a result could not be replicated, each time a signature faded into statistical ambiguity, each time a negative finding emerged, even if the negative rested on less sophisticated methodology or ambiguous stratigraphy. It became about gatekeeping. Editors favored reviews that were skeptical, published negative replications more quickly than positive ones, allowed harsh language most studies would never accept. Once the narrative of probably not real gained momentum, it became harder and harder for new evidence to change minds. Even for solid replication studies that matched all the required markers, the burden of proof was set impossibly high. Some began to wonder if only a 100-kilometer comet crater in downtown Chicago would ever make the skeptics budge. Behind closed doors, some admitted privately the evidence was striking, even troubling, but not quite enough yet to tip the scales. The premature rejection, as James Lawrence Powell would later call it, became not just a case study in this field, but a broader lesson in how science sometimes moves more slowly than the evidence would allow. Science advances one funeral at a time, the old adage goes. For some, it felt like funerals, reputations, careers, even opportunities for truth were piling up faster than answers. A small group of senior scientists, caught between the noise, acted as something like referees. They called for patience. They published cautious reviews, weighed the merits, refused to dismiss the idea outright, but also refused to let it overrun younger minds hungry for revolution. Their attitude was, in essence, time and data will decide. But data collection is never neutral. It costs money, time, attention, and all of those depend on gatekeeping by the same structures caught up in the debate. As public interest increased, media outlets ran with the drama. Documentaries about the comet that ended the Ice Age brought the story into living rooms. Popular science books touted the crisis, spun tales that reached millions online. College freshmen read about Firestone's team in general science surveys. Critics worried that even a bad theory could do real damage if it bled far enough from the lab to the street, worried, at times, about their own credibility, about their ability to keep the line between evidence and myth from blurring in the public mind. Through it all, the lines hardened. Skeptics and proponents built networks, wrote joint letters, challenged opposing grants, collaborated on special journal issues. The hypothesis became a lens, a way to view the sociology of science in real time. Who published with whom, who cited whom, even who shared hotel rooms at annual meetings, all became data points in a struggle that was about more than black mats and nanodiamonds. For Firestone and his allies, the constant pushback hardened their sense of being under siege. Some embraced a narrative of scientific martyrdom, others doubled their focus, hunting for ever more compelling proxies, running more rigorous tests, expanding the search for evidence worldwide. They knew the cost of sticking with the idea was high. Even if they won, it might come too late for their own careers. Meanwhile, the evidence kept growing, now including shock metamorphic features, microspherules, and geochemical markers found precisely at the yard boundary in 4 continents. Advocates pointed out that almost no credible alternative had been proposed that fit the worldwide synchronous datelines, that explained the sudden extinction pulses, the simultaneous environmental fires, the cultural turnovers. Critics kept raising the bar, sometimes, it seemed, just beyond whatever the proponents had achieved. When new studies reanalyzed old negative sites, applying stricter stratigraphic control, improved radiometric dating, more selective sampling, positive results often emerged. But by then, the myth of irreproducibility had become canon. To the press, the story was now two sides with intractable views. To young scientists, it was a warning lesson: tread carefully. Peer review became more adversarial. Papers supporting the hypothesis faced multiple rounds of critical review, demands for data far beyond normal standards. Dissenters faced their own skepticism, but sometimes only from a shrinking group of believers. An atmosphere of mutual contempt threatened to undermine an entire field's ability to self-correct, to learn, to change as new facts emerged. For some, the most troubling sign was how much the controversy began to poison other questions. Funding dried up not just for direct impact research, but for paleoclimate work that might even touch on the boundaries of debate. Paleontologists working on mammoth extinctions, archaeologists hunting pre-Clovis sites, climatologists studying rapid climate changes all found their work scrutinized, sometimes dismissed, if it seemed to lend inadvertent support to a discredited hypothesis. The longer the controversy went on, the more it began to echo older scientific wars: continental drift, evolutionary theory, even early studies of human-caused climate change. Each had gone through its phase of ridicule, marginalization, argument, and often eventual acceptance. Critics and champions alike invoked history. It took a generation to accept plate tectonics, they say. Maybe, eventually, the data will win. Proponents countered, isn't the mark of mature science the willingness to change when faced with new facts? But data is only as useful as those who interpret it. When careers depend on consensus, when research funding is scarce, when journals lock out controversy for fear of being ridiculed, the search for truth can get lost. The Younger Dryas Impact war became not just a fight about one theory, but a test case for the culture of science itself, a living demonstration that discoveries, if disruptive enough, require not just evidence, but a paradigm shift in the institutions carrying the torch of knowledge. In this war, evidence was necessary, but not always sufficient. The gatekeepers insisted, sometimes reasonably, sometimes not, that the standard for revolution had to be higher than usual, that extraordinary claims required extraordinary proof. The longer it went, the more the climate for debate cooled, a fitting metaphor for a theory centered on sudden cold. And so, the story arrived at stalemate. Journals, conferences, funders, and universities waited, more interested in caution than resolution. New findings might shift the field suddenly, but no one could predict when, or even if, the sudden revolution might come. Until then, the Younger Dryas Impact hypothesis stood as both a riddle in ancient sediment and a living, modern parable of how change comes, slowly, then all at once. And how science, as human as its practitioners, sometimes struggles to see what is right beneath the surface. Every ancient culture remembered something. Not everything, not the same details, not with the same words or symbols or gods presiding over the narrative. But they all remembered the sky falling, the water rising, the world ending and beginning again. More than 200 independent cultures across every inhabited continent preserved stories of catastrophic floods, of fire from heaven, of darkness covering the earth, of a time when most of humanity died and only a few survived to rebuild. These weren't borrowed stories, weren't tales spread by trade or conquest, weren't myths copied from one culture to another as populations migrated and mingled. They were too old for that, too deeply embedded in separate traditions, too specific in their local details while sharing the same global themes. The Sumerians, who wrote down their stories in cuneiform on clay tablets 5,000 years ago, told of Ziusudra, the man who survived the Great Deluge by building a massive boat according to divine instructions. The flood came, lasted 7 days and 7 nights, destroyed all life except what Ziusudra had preserved on his vessel. When the waters receded, when the world dried and life could begin again, Ziusudra offered sacrifice and was granted immortality by the gods who had sent the flood. The story was ancient even when the Sumerians recorded it, was old enough that they called it a tale from the time before the first dynasty, from the days when the gods walked the earth and taught humans the arts of civilization. The Epic of Gilgamesh, written down later in Akkadian but drawing on Sumerian sources even older, told the same story, with more detail, with more drama, with language that still resonates across 4,000 years. Utnapishtim, the flood survivor in this version, described the disaster with specificity that sounds less like myth and more like eyewitness testimony filtered through generations of retelling. The gods decided to destroy humanity through flood, but one god warned Utnapishtim, told him to build a boat, told him to save his family and representatives of all living creatures. The storm came with fury beyond description, darkness covered the world, the gods themselves cowered in terror at what they had unleashed. For 6 days and 6 nights the flood continued, winds howled, waters rose, everything humanity had built was swept away. On the 7th day the storm subsided, the waters began to recede, the boat came to rest on a mountain peak. Utnapishtim sent out birds to search for dry land, watched them return again and again until finally one did not come back, proving that somewhere the world had emerged from beneath the waters. The description includes details that shouldn't be there if this were pure invention, includes observations about bird behavior, and storm patterns and flood dynamics that suggest someone, somewhere, actually experienced something like this and the memory persisted. The Hebrew Bible preserved similar accounts in Genesis, told of Noah and the ark, of 40 days and 40 nights of rain, of a flood that covered the highest mountains and destroyed all life except what Noah had saved. Scholars have long noted the parallels with Sumerian and Babylonian flood myths, have debated whether the biblical account borrowed from Mesopotamian sources or whether both drew on common older traditions. But the question isn't whether Jews borrowed from Sumerians or vice versa, the question is why these stories exist at all, why separate cultures felt compelled to preserve memories of catastrophic floods in such specific detail. The Greeks remembered Deucalion, who survived a flood sent by Zeus to destroy the corrupt bronze race of humanity, who built a chest that carried him and his wife to safety, who repopulated the earth by throwing stones that became new humans. The Hindus told of Manu, warned by a fish that grew to enormous size, who built a ship that survived the deluge and became the progenitor of the new human race. The Chinese preserved stories of Gunyu taming the Great Flood, of waters that reached the heavens and destroyed the world until heroes intervened to channel them back into proper courses. But these old world flood myths, as striking as they are, don't prove anything about a real global catastrophe, don't necessarily point to the Younger Dryas Impact, could be explained through local floods along major rivers, where early civilizations developed. The Tigris and Euphrates flood regularly, the Yellow River has caused devastating floods throughout Chinese history, the Indus and Ganges have their own histories of catastrophic flooding. Maybe these stories just reflect cultural memories of regional disasters, exaggerated through retelling, mythologized into cosmic events that were actually just bad floods in specific river valleys. Except the Americas tell the same stories, preserve the same memories, describe the same events despite having no contact with old world civilizations when these stories were first being told. Native American flood myths span both continents, appear in traditions separated by thousands of miles, describe catastrophes that match the Mesopotamian accounts in their essential elements even while differing in specific details and local framing. These stories couldn't have been borrowed from Middle Eastern sources, couldn't have been influenced by biblical narratives, existed in oral traditions long before Columbus arrived and European settlers began their genocidal conquest. The Ojibwe people of the Great Lakes region told of a great flood sent to cleanse a world that had become corrupt, of Nanabojo who survived by floating on a log with various animals, who eventually found land and recreated the world. but their stories also mentioned fire from the sky before the flood, mentioned stars falling and the earth shaking, mentioned details that sound less like normal flooding and more like the kind of catastrophic impact event that researchers were documenting in the geological record. The stars fell, the story said, fell in great numbers, fell with fire that burned everything, and then the waters came and covered what the fire had left behind. The Hopi of the Southwest preserved stories of multiple world ages, of destructions and renewals, of times when the world ended and new worlds began. The Third World, they said, was destroyed by flood and fire together, by catastrophes that came from the sky, by disasters that killed most of humanity and forced the survivors to find refuge in the Fourth World, the current world, the world we inhabit now. Their stories described people being warned, being told to find high ground or deep caves, being advised to seek shelter before the destruction came. Only those who listened survived, only those who found proper refuge lived to tell the tale, only those who preserved the knowledge could pass it down to future generations. The Iroquois Confederacy told similar stories, described world destruction through fire and flood, through catastrophes that came with little warning, through disasters that tested whether humans deserved to continue existing. Their stories emphasized that survivors were chosen for their virtue, for their respect for the old ways, for their willingness to preserve knowledge and pass it to their children. This theme appears consistently across Native American flood myths, this idea that survival wasn't random, wasn't just luck, wasn't purely a matter of who happened to be in the right place. Survival was moral, was spiritual, was about preserving what was important and ensuring that future generations would remember what had been lost. South American traditions preserved even more dramatic accounts, told stories that matched the geological evidence for Younger Dryas effects in the southern hemisphere almost perfectly. The Mapuche people of Chile described Cai and Tren, two great serpent spirits that fought, one bringing floods that drowned the world, the other raising mountains to save the people. But before this battle, they said, fire fell from the sky, great stones crashed into the earth, the world shook and split, and darkness covered everything for many days. People fled to the highest peaks, climbed mountains that rose even as they ascended, watched as the lowlands filled with water and everything they had known disappeared beneath waves. The Muisca people of Colombia told of Bochica, a bearded teacher who appeared after the great catastrophe, who helped survivors rebuild, who taught them agriculture and architecture and astronomy, who gave them knowledge that their ancestors had possessed before the destruction. This pattern appears repeatedly in post-flood myths worldwide, this arrival of wise teachers who seem to possess advanced knowledge, who appear after catastrophes to help survivors rebuild, who establish the foundations of what would become great civilizations. The stories suggest these teachers weren't gods but survivors from whatever civilization had existed before the flood, survivors who had knowledge worth preserving, survivors who took responsibility for ensuring that not everything was lost. The Inca inherited stories from earlier Andean cultures, preserved memories of Viracocha who rose from Lake Titicaca after the Great Flood, who brought order to a chaotic world, who created the sun and moon and stars, and taught humanity how to live in proper relationship with nature. The stories emphasized that Viracocha came from the water, came after the destruction, came when the world needed rebuilding. The timing matters, the sequence of events matters, the pattern of catastrophe followed by reconstruction led by knowledgeable teachers matches what you'd expect if an advanced culture had been destroyed by the Younger Dryas Impact and survivors had scattered to help less affected populations rebuild. Egyptian mythology preserved similar themes in different symbolic language, told of the first time when gods walked the earth, when the Nile flowed backwards, when chaos overwhelmed order, when none, the primordial waters, covered everything. The pyramid texts, the oldest religious texts from Egypt, describe this period with language that sounds catastrophic rather than purely mythological, described events that seem to be memories filtered through theological interpretation rather than pure invention. The text spoke of the sky falling, of fire and water together, of darkness and destruction followed by rebirth under the guidance of divine teachers who re-established cosmic order, after chaos nearly destroyed everything. The Aboriginal Australians, isolated from other continents for 50,000 years, preserved stories of the dream time when the world took its current shape, when massive floods and fires reshaped the landscape, when sea levels rose and swallowed coastal plains where ancestors had lived for generations. Their stories contained remarkable geological accuracy, described specific changes in coastline and river systems that archaeological evidence confirmed had actually occurred during the terminal Pleistocene. They remembered, with precision that startled geologists when they finally paid attention, exactly which valleys had been flooded when sea levels rose after the Ice Age, exactly which islands had been connected to the mainland before the waters came. This accuracy suggests these weren't just myths, weren't symbolic stories, weren't purely spiritual narratives divorced from physical reality. These were memories, cultural memories preserved through oral tradition for thousands of years, memories specific enough that they could be matched to actual geological events when modern science finally developed tools to investigate. If Aboriginal Australians could preserve accurate memories of coastline changes from 10,000 years ago, if their stories matched the archaeological and geological record so precisely, then why shouldn't we take seriously the possibility that other cultures were also preserving real memories, also passing down accounts of actual events even when those accounts were wrapped in mythological language and theological interpretation? The Polynesian peoples, who navigated the Pacific Ocean in voyages that modern sailors struggle to replicate, preserved stories of great floods, of islands sinking, of the sea rising to swallow lowlands, of times when the ocean was angry and destroyed what had been built. They told of Paio and other voyagers who carried knowledge from destroyed homelands to new islands, who established colonies after catastrophes, who preserved sacred knowledge that might have been lost if they hadn't fled. Their navigation skills alone prove they possessed sophisticated knowledge, prove they were capable of preserving and transmitting complex information across generations, prove they shouldn't be dismissed as primitive storytellers whose myths bear no relationship to reality. The global distribution of these flood myths matters more than mainstream archaeology has been willing to admit, matters as evidence that something real happened that was catastrophic enough to imprint itself on human cultural memory worldwide. The timing matters too, when archaeological dating techniques can estimate when these stories originated, when linguistic analysis can trace how long oral traditions have been preserved, when the evidence suggests these myths are genuinely ancient rather than recent inventions or borrowings. The similarities matter, the specific details that appear across cultures that had no contact with each other, the patterns that match the geological and archaeological evidence for Younger Dryas impacts and their effects. Critics dismiss flood myths as evidence, claim they prove nothing, argue they're just stories people tell, natural responses to local flooding, universal myths that cultures develop independently because floods happen everywhere and make good cautionary tales. But this dismissal ignores the specificity, ignores the timing, ignores the patterns that emerge when you actually examine these stories carefully rather than waving them away as primitive superstition. The myths describe fire from the sky, describe sudden catastrophes rather than gradual events, describe survivals that required preparation and warning, describe teachers who appeared after the destruction to help rebuild. These aren't generic flood stories, aren't simple river overflow narratives, aren't myths that could be explained by normal meteorological events and local disasters. They're memories of something global, something catastrophic, something that forced a reset of human civilization, something that killed most people and required survivors to start over with whatever knowledge they could preserve. They're memories, passed down through 10,000 years of oral tradition, memories of the moment when the sky fell and the world burned and the waters rose and humanity nearly ended. They're memories of the Younger Dryas impact, whether modern science wants to admit it or not, whether academic, gatekeepers will allow the comparison or not, whether accepting the connection threatens comfortable narratives about how civilization developed, gradually through steady progress rather than being forced to rebuild after catastrophic collapse. The question haunted Graham Hancock for decades, kept him awake at night, drove him to archaeological sites across every continent, pushed him to ask uncomfortable questions that mainstream academics refused to consider. If the Younger Dryas Impact happened, if it really destroyed megafauna and ended the Clovis culture and triggered global climate catastrophe, what else might it have destroyed? What other human societies might have existed before that moment, societies sophisticated enough to leave behind knowledge but unlucky enough to be annihilated so thoroughly that only fragments survived, only hints remained, only myths preserved their memory? The standard narrative of human civilization is simple, linear, comforting in its progression from primitive to advanced. Humans lived as hunter-gatherers for hundreds of thousands of years, then discovered agriculture around 10,000 years ago, in the Fertile Crescent, then built the first cities in Mesopotamia around 5,000 years ago, then developed writing and mathematics and architecture and all the accomplishments we associate with civilization. It's a story of steady progress, of gradual accumulation of knowledge, of humanity slowly climbing from Stone Age simplicity to Bronze Age complexity to our modern technological world. It's a story that makes sense, that fits the evidence we've been taught to see, that supports the academic careers built on studying this progression. But it's also a story that requires ignoring uncomfortable anomalies, that demands dismissing evidence that doesn't fit, that insists we explain away structures and artifacts and knowledge that shouldn't exist according to the timeline. Göbekli Tepe in Turkey, discovered in the 1990s and dated to 11,600 years ago, features massive stone pillars arranged in circles, decorated with sophisticated carvings of animals and abstract symbols, constructed by people who supposedly hadn't invented agriculture yet, hadn't developed the complex social organization that creating such monuments should require. The site predates Stonehenge by 6,000 years, predates the pyramids by 7,000 years, exists in a time period when humans were supposed to be scattered bands of hunters with no architectural achievements beyond simple shelters. The excavator, Klaus Schmidt, spent his career trying to explain how this was possible, how hunter-gatherers could have mobilized the labor and developed the skills to quarry and transport stones weighing up to 20 tons, to carve them with precision that still impresses modern sculptors, to arrange them in geometric patterns that suggest astronomical knowledge and abstract thinking we're told humans hadn't developed yet. His explanations involved invention of new theories about social organization, proposals that maybe religion came before agriculture rather than after, suggestions that the need to gather for ceremonial purposes at places like Göbekli Tepe actually drove the development of farming rather than farming enabling monument construction. These theories strained credibility, required special pleading, demanded that we believe humans suddenly developed capabilities they'd never shown before and would barely use again for thousands of years. But the alternative was worse, was unthinkable within mainstream archaeology, was a possibility that threatened the entire edifice of accepted chronology. The alternative was that Göbekli Tepe wasn't the beginning of civilization but a remnant, wasn't the first monument, but one of the last survivors from something older, wasn't evidence of hunter-gatherers suddenly becoming sophisticated but evidence of sophisticated people being reduced to survival level by catastrophe. That catastrophe, Hancock argued, was the Younger Dryas Impact. The timing aligned perfectly, impossibly perfectly. Göbekli Tepe was constructed just after the Younger Dryas ended, built in the centuries following the climate chaos and megafauna extinctions and cultural collapse that the impact had triggered. If a civilization had existed before the impact, if it had been destroyed by comet fragments and fires and floods and climate disruption, then survivors would have scattered, would have sought refuge in regions that escaped the worst effects, would have tried to preserve whatever knowledge they could salvage from the ruins. They would have built monuments, would have established centers where that knowledge could be maintained, would have attempted to restart civilization even though they lacked the resources and population to fully reconstitute what had been lost. This interpretation explained Göbekli Tepe better than the mainstream narrative did, explained why the site appeared fully formed, with no apparent developmental sequence, explained why the oldest structures at the site were actually the most sophisticated, while later construction showed declining quality, explained why the people who built it seemed to possess knowledge that they shouldn't have had according to conventional timelines. It wasn't the dawn of civilization, it was the twilight, the last gasp of knowledge being preserved before it slipped away entirely as survivor populations diminished and the trauma of catastrophe made transmission of complex information increasingly difficult. Egypt presented similar puzzles, similar evidence of knowledge appearing where it shouldn't, of capabilities existing before they should have been developed. The Great Pyramid of Giza, conventional Egyptology insisted, was built around 2560 BCE as a tomb for Pharaoh Khufu using copper tools and wooden rollers and unlimited corvée labor. This narrative required believing that a civilization with no previous experience building anything remotely comparable suddenly constructed the largest stone structure in the world with precision that modern engineers struggle to replicate, aligned it to true north with accuracy that exceeds most modern buildings, incorporated mathematical relationships including pi and phi that Egyptians supposedly hadn't discovered yet, achieved all this within a single pharaoh's reign of perhaps 23 years. Robert Schoch, the geologist who examined the Sphinx and concluded it showed water erosion patterns indicating it was far older than conventional dating allowed, extended his analysis to the broader Giza complex. The precision of the pyramid's construction, he argued, exceeded what Bronze Age technology should have achieved. The blocks weren't just large, they were fitted with tolerances measured in fractions of an inch, joined so perfectly that you couldn't slip a razor blade between them, shaped with techniques that required understanding of stone, properties that came from long experience. The mathematics embedded in the structure's proportions suggested knowledge that shouldn't have existed in 2560 BCE, suggested builders who understood geometry and astronomy and physics at levels that conventional chronology claimed weren't reached for another 2,000 years. The Sphinx, even more than the pyramids, challenged accepted timelines. Its water erosion, if Schoch's analysis was correct, meant it had been exposed to heavy rainfall for extended periods, rainfall that hadn't occurred in the Giza region since the end of the last ice age, since the climate shift that followed the Younger Dryas. This would place the Sphinx's construction at least 9,000 years before present, perhaps even older, making it contemporaneous with Göbekli Tepe, making it another monument built in that narrow window after the impact when survivors were still capable of sophisticated construction, still possessed knowledge from before the catastrophe, still remembered how to build on scales that later generations would struggle to match. The Egyptian priests told Herodotus and Plato and other Greek visitors that their civilization was far older than Greeks imagined, that the temples and monuments they saw were recent compared to the true antiquity of Egypt, that knowledge had been preserved from the first time when gods walked the earth and taught humanity the foundations of civilization. These stories were dismissed as mythological, as priestly propaganda inflating Egypt's importance, as religious narratives that bore no relationship to historical reality. But what if the priests were telling the truth? What if their temple archives really did preserve records stretching back thousands of years before the first dynasties? What if the gods they remembered were actually survivors from a pre-impact civilization who appeared to primitive populations as divine teachers because their knowledge seemed supernatural? Plato's account of Atlantis, written around 360 BCE, claimed to be based on information the Athenian statesman Solon had received from Egyptian priests at Sais. The priests told Solon that 9,000 years before their conversation, a great civilization had existed on an island beyond the Pillars of Hercules, a civilization that had achieved remarkable technological sophistication, that had built a vast empire, that had become corrupt and aggressive and had finally been destroyed in a single day and night of earthquakes and floods that caused the island to sink beneath the waves. The destruction, according to the Egyptian chronology Plato preserved, occurred around 9600 BCE, give or take a few centuries depending on how you interpret the Greek calendar system he was using. That date, that specific time frame, corresponded almost exactly with the end of the Younger Dryas, with the period when climate was stabilizing after 13 centuries of cold, with the moment when sea levels were rising rapidly, as ice sheets finally melted, with the transition from Pleistocene to Holocene that marked the beginning of the modern climatic period. The coincidence was too precise to ignore, too well aligned with both the impact timing and the subsequent climate changes to be mere accident. If Atlantis was real, if it was a genuine historical civilization rather than Plato's philosophical invention, then the Younger Dryas Impact provided a mechanism for its destruction that matched the catastrophic timeline Plato described. Mainstream academics dismissed Atlantis as fiction, as allegory, as Plato's thought experiment about ideal versus corrupt societies rather than any kind of historical account. They pointed out that no archaeological evidence for such a civilization had ever been found, that no ruins of advanced cities had been discovered on any Atlantic islands, that the story contained elements that seemed mythological rather than historical. But this critique ignored the possibility that evidence might have been destroyed by the very catastrophe that ended the civilization, ignored that sea level rise of over 100 meters since the Younger Dryas would have submerged coastal civilizations entirely, ignored that 13,000 years of geological change would have buried or eroded whatever wasn't underwater. Hancock proposed that the real Atlantis, if it existed, wasn't a single island but a global maritime civilization, a network of coastal settlements and trading posts linked by seafaring capabilities that, we're told, humans didn't possess in the terminal Pleistocene. This civilization would have concentrated in areas that are now underwater, would have built on continental shelves that were exposed during the Ice Age when sea levels were lower, would have been wiped out when the Younger Dryas Impact triggered meltwater pulses that raised oceans and flooded coastlines worldwide. Survivors would have fled inland, would have settled in regions like Turkey and Egypt and the Andes, would have built monuments like Göbekli Tepe and the Sphinx to preserve knowledge from the lost civilization. The evidence for sophisticated pre-Younger Dryas cultures kept accumulating despite academic resistance, kept appearing in contexts that conventional chronology struggled to explain. Gunung Padang in Indonesia, a massive terraced pyramid investigated by geologist Danny Hillman Natawijaya, showed construction phases that carbon dating and ground-penetrating radar suggested extended back 20,000 years or more, far beyond when humans supposedly possessed architectural capabilities. The oldest layers showed precisely shaped columns arranged in geometric patterns, showed evidence of advanced construction techniques, showed sophistication that shouldn't exist in Southeast Asia during the late Pleistocene. Underwater structures off the coast of Yonaguni in Japan, discovered by dive tour operator Kihachiro Aratake in 1987, featured what appeared to be carved terraces, steps, roads, and monuments submerged beneath 70 feet of water. Geologist Robert Schoch examined the site, concluded that while some features might be natural, others showed evidence of human modification, showed tool marks and geometric arrangements that were difficult to explain through pure geology. The structures would have been above water during the Ice Age, would have been submerged when sea levels rose after the Younger Dryas, would represent exactly the kind of coastal civilization that Hancock's hypothesis predicted. Dwarka off the coast of India, a submerged city that Indian archaeologists discovered using side-scan sonar, showed similar evidence of pre-flood construction, showed walls and structures beneath the Arabian Sea that matched descriptions in ancient Hindu texts of a great city that sank beneath the waves. The Mahabharata and other Sanskrit epics described Dwarka as the capital city of Krishna, described it being swallowed by the ocean after Krishna's death, described events that conventional scholars dated to myth but that marine archaeology was now confirming had some historical basis. The Bimini Road in the Bahamas, two parallel lines of rectangular limestone blocks stretching for half a mile underwater, generated controversy since its discovery in 1968. Geologists argued it was natural, was beach rock formation that coincidentally resembled human construction. But the blocks showed evidence of tool marks, showed alignments too regular to be random, showed features that suggested human modification even if natural processes had contributed to the formation. The structure would have been above water when sea levels were lower, would have been submerged by the same post-Younger Dryas sea level rise that flooded other coastal areas, would fit the pattern of a maritime civilization destroyed by rising oceans. All of these sites, scattered across different continents and different oceans, showed the same pattern, suggested the same conclusion that mainstream archaeology refused to accept. Sophisticated construction in time periods before civilization supposedly existed, monuments and structures that were either incredibly old or required rewriting what we thought we knew about human capabilities during the terminal Pleistocene, evidence that kept accumulating, despite being dismissed as anomalous or misinterpreted or simply impossible according to accepted chronology. The resistance to these findings wasn't just scientific skepticism, wasn't just careful evaluation of evidence before accepting revolutionary claims. It was defensive, was protective of established narratives, was driven by institutional interests and academic politics as much as by genuine concern about maintaining scientific rigor. Accepting that advanced civilizations existed before the Younger Dryas would require rewriting textbooks, would invalidate decades of research built on gradualist models of human development, would threaten the careers and reputations of scholars who had spent lifetimes building expertise in chronologies that would suddenly become obsolete. But the evidence didn't care about careers, didn't respect academic consensus, didn't vanish just because it was inconvenient. The monuments remained, the underwater structures persisted, the anomalous artifacts continued to emerge from excavations and surveys. The myths remembered, the flood stories preserved memories of catastrophe and destruction and civilizations lost beneath the waves. The geological record showed the Younger Dryas Impact, showed the climate chaos and extinction events and cultural collapses that followed. And the pattern, when you step back far enough to see it whole, suggested something that conventional archaeology had missed, something that required catastrophe to explain, something that pointed toward lost civilizations and preserved knowledge and survivors trying desperately to rebuild what the comet had destroyed. The door beneath the Sphinx remained sealed, the hall of records stayed hidden, the evidence that might prove everything stayed buried. But the questions wouldn't go away, the anomalies kept multiplying, and the possibility that we'd forgotten our own history became harder to dismiss with each new discovery that didn't fit the comfortable narrative we'd been taught to believe. They appeared after the catastrophe, emerged from the chaos and devastation like figures from myth, arrived in different lands with knowledge that shouldn't exist, with skills that survivors couldn't explain, with wisdom that seemed divine rather than human. Every culture that preserved flood memories also preserved stories of these teachers, these mysterious figures who came after the waters receded, who helped rebuild what the catastrophe had destroyed, who established the foundations of civilization in lands where civilization supposedly hadn't existed before. The mainstream narrative dismisses them as gods, as mythological constructs, as symbolic representations of cultural values rather than actual historical figures. But what if they were real? What if they were survivors? What if they were the last remnants of whatever civilization the Younger Dryas Impact had destroyed? Viracocha walked out of Lake Titicaca, according to Andean tradition, emerged from the waters at Tiwanaku after the Great Flood had subsided, after the world had been destroyed and needed rebuilding. He was described as tall, bearded, light-skinned, distinctly different in appearance from the indigenous populations of the region. He traveled across the Andes teaching agriculture, teaching architecture, teaching astronomy, establishing the foundations of what would eventually become the Inca Empire, though he predated that empire by thousands of years. The stories emphasized that he came from before, that he possessed knowledge from the previous world, that he was trying to preserve what could be saved from the destruction that had ended the age of giants and flooded the coastal cities. The timing matters more than academics have been willing to acknowledge, matters because Tiwanaku and the broader Lake Titicaca region show evidence of sophisticated construction that predates conventionally accepted timelines for Andean civilization. The massive stone blocks at Pumapunku, fitted with precision that modern masons struggle to replicate, carved with techniques that shouldn't exist in pre-Columbian America, arranged in patterns that suggest astronomical knowledge and engineering capabilities that appeared fully formed without apparent developmental sequence. These weren't the products of gradual cultural evolution, weren't the result of centuries of trial and error, weren't monuments built by people slowly learning how to work stone and design structures. These were the products of knowledge, of expertise, of skills that seemed to arrive complete as if transmitted by teachers who already knew what they were doing. Quetzalcoatl appeared in Mesoamerica with similar characteristics, similar knowledge, similar mystery about his origins. The Aztecs and Maya remembered him as the feathered serpent, the bearded teacher who came from across the sea, who brought knowledge of mathematics and astronomy and agriculture, who taught the calendar systems that allowed Mesoamerican civilizations to track time with precision that rivaled anything achieved in the Old World. He was described as light-skinned, as bearded when indigenous populations typically weren't, as distinctly foreign in appearance despite arriving so long ago that his time was considered the age of gods rather than the age of men. The Maya calendar that Quetzalcoatl allegedly taught was astronomically sophisticated, tracked multiple cycles simultaneously, predicted eclipses and planetary positions with accuracy that required centuries of careful observation to develop. Yet it appeared early in Maya cultural development, showed up without clear antecedents, existed as a complete system rather than something gradually refined over generations. This pattern matched Viracocha and the Andean knowledge, matched the sudden appearance of capabilities that should have required long development periods, matched what you'd expect if teachers from a destroyed advanced civilization were transmitting preserved knowledge to surviving populations. Thoth in Egypt fulfilled the same role, appeared in the Egyptian pantheon as the god of wisdom and writing, as the divine scribe who recorded the deeds of the dead, as the inventor of hieroglyphs and mathematics and astronomy. But beneath the theological overlay, beneath the religious symbolism that accumulated over millennia, the original Thoth stories described a teacher, described a figure who brought knowledge after a great catastrophe, described someone who established the foundations of Egyptian civilization during the first time, the Zep Tepi, the primordial age when gods walked the earth, before the dynasties began. The pyramid texts, the oldest religious writings from Egypt, preserved in 5th and 6th dynasty pyramids but clearly drawing on much older sources, referenced this first time repeatedly, described it as the age when divine beings taught humanity the arts of civilization, when the foundations were laid that later Egyptian culture would build upon. The text spoke of the followers of Horus, of the Shemsu Hor, beings who bridged the gap between the gods and humans, who preserved divine knowledge through the catastrophes that separated the first time from the dynastic period, who ensured that what had been learned before the flood wouldn't be entirely lost. Oannes emerged from the Persian Gulf according to Babylonian tradition, described by the priest Berossus, in accounts that survived only through Greek and Roman quotations. Oannes was amphibious, spent days teaching the Sumerians during daylight hours, returned to the sea at night, appeared every morning, to continue instruction in writing and agriculture and law and architecture. The description sounds mythological, sounds like pure invention, sounds like the kind of story people tell, to explain the mysterious origins of their civilization. But strip away the fantastic elements, remove the supernatural overlay, and what remains is a memory of teachers arriving from the sea, arriving after some catastrophe, arriving with knowledge they transmitted to populations that desperately needed it. The Dogon people of Mali, studied by French anthropologists Marcel Griaule and Germaine Dieterlen in the 1930s and 40s, preserved stories of the Nomo, amphibious beings who arrived from the sky in an ark, who taught the Dogon astronomy and agriculture, who established their culture and then departed. The anthropologists were stunned to discover that Dogon astronomical knowledge included information about Sirius B, the white dwarf, companion star to Sirius that's invisible to the naked eye and wasn't detected by Western astronomy until 1862. The Dogon knew its orbital period, knew it was dense and small, knew details that required telescopic observation to discover. Where did this knowledge come from? How did pre-literate West African people acquire information that European astronomers only learned through advanced instruments? The skeptics proposed contamination, suggested that Dogon elders had somehow learned about Sirius B from Western visitors and incorporated it into their traditional stories, argued that the anthropologists had been deceived or had misunderstood what they were told. But Griaule and Dieterlen documented the knowledge carefully, spent years learning Dogon oral traditions, verified that the astronomical information was embedded in religious stories that predated any European contact. The simplest explanation, the one that made sense if you were willing to question assumptions about primitive cultures, lacking sophisticated knowledge, was that the Dogon had preserved accurate astronomical information transmitted from an earlier time, from teachers who possessed observational capabilities that later populations lost. The pattern repeated across every continent, appeared in every culture that survived the catastrophe, showed up in traditions separated by oceans and mountains and thousands of miles. The Polynesians told of Maui, the culture hero who taught navigation and fishing, who established the foundations of the seafaring culture that would eventually spread across the entire Pacific. The Aboriginal Australians preserved stories of the Wangina, spirit beings who came during the dream time, who taught proper relationship with the land, who established the song lines that encoded geographical and cultural knowledge. The Maori of New Zealand remembered the arrival of the Great Fleet, remembered teachers who brought knowledge from across the ocean, remembered foundations laid by those who came before. These teachers weren't described as ordinary humans, weren't portrayed as local heroes who invented things through trial and error, weren't presented as gradual cultural evolution personified. They were foreigners, were outsiders, were beings who possessed knowledge from elsewhere, from before, from a time when the world was different. They appeared after catastrophes, after floods, after the world had ended and needed rebuilding. They established foundations quickly, transmitted complex knowledge efficiently, created cultural systems that seemed to arrive complete rather than developing gradually over generations. The mainstream interpretation treats all this as mythology, as religious symbolism, as cultural constructs that tell us about how ancient people viewed their own origins but that bear no relationship to actual history. But this interpretation requires dismissing the specificity, requires ignoring the patterns, requires explaining away the suspicious alignment between flood myths and teacher myths and evidence of sophisticated knowledge appearing suddenly in cultures that supposedly shouldn't possess it. It requires believing that dozens of independent cultures all invented the same basic story through pure coincidence, all decided to attribute their cultural foundations to mysterious foreign teachers who appeared after catastrophes, all preserved memories of events that never happened in essentially the same way despite having no contact with each other. The alternative explanation, the one that makes sense if you're willing to question academic orthodoxy, is that these stories preserve real memories, that the teachers were actual people, that they were survivors from whatever civilization the Younger Dryas Impact had destroyed. They would have been scattered, would have found refuge in regions that escaped the worst effects, would have encountered populations of hunter-gatherers who had survived the catastrophe but who lacked the complex knowledge that the destroyed civilization had possessed. These survivors, these refugees from drowned coastal cities and burned settlements, would have possessed skills that seemed magical to less sophisticated populations, would have been treated as gods or demigods, would have been remembered in myths and legends long after they died and their true origins were forgotten. They would have tried to preserve knowledge, would have understood that their civilization was gone and wouldn't be fully reconstituted in their lifetimes, would have attempted to transmit whatever they could to the populations that survived. They would have taught agriculture because farming was essential for rebuilding stable societies. They would have taught astronomy because tracking seasons and predicting celestial events was crucial for agriculture and navigation. They would have taught mathematics and writing because complex knowledge couldn't be preserved through oral tradition alone, needed recording systems and numerical frameworks to survive transmission across generations. They would have taught architecture because permanent structures were necessary for civilizations that hoped to last, because building in stone created monuments that would outlast the builders and carry their knowledge forward. The monuments they built or inspired others to build would have served multiple purposes, would have been more than just temples or tombs, would have functioned as time capsules, as encoded repositories of knowledge, as structures designed to survive catastrophes and preserve information for future generations. The Great Pyramid's mathematical relationships, the astronomical alignments at sites like Göbekli Tepe and Tiwanaku, the geometric patterns at places like Teotihuacan and Angkor Wat, all suggested that these monuments were encoding knowledge, were preserving information in forms that couldn't be easily destroyed, were attempting to ensure that future civilizations would have access to what earlier civilizations had learned. This interpretation explained why so many ancient monuments seemed over-engineered, seemed to employ techniques and precision far beyond what their stated purposes required, seemed to incorporate mathematical and astronomical knowledge that conventional chronology insisted their builders shouldn't possess. They weren't just tombs or temples, weren't just religious structures or royal vanity projects, weren't built solely for the purposes that later cultures attributed to them. They were messages, were libraries in stone, were attempts by survivors of the catastrophe to encode and preserve knowledge that might otherwise be lost as the last generation who remembered the pre-impact civilization died off. The Hall of Records beneath the Sphinx, if it existed as Edgar Cayce had predicted, would be the ultimate expression of this impulse, would be the deliberate preservation of knowledge in a vault designed to survive millennia, would be proof that survivors of the Younger Dryas Impact had intentionally created time capsules for future generations to discover. The Egyptian authorities' refusal to allow excavation, their resistance to investigations that might confirm the hall's existence, suggested they knew something, knew what might be found, knew that discovery would force revision of everything we thought we understood about human history and the origins of civilization. The knowledge keepers died eventually, died without fully reconstituting what had been lost, died knowing that their civilization had ended and wouldn't return in anything like its original form. But they left traces, left monuments, left stories, left encoded knowledge in structures and myths and traditions that survived long enough for modern researchers to begin decoding them. They left questions that mainstream archaeology couldn't answer, left anomalies that conventional chronology couldn't explain, left evidence that kept accumulating despite academic resistance, despite institutional gatekeeping, despite all the reasons that established authorities might prefer the comfortable narrative of gradual cultural evolution to the disturbing possibility that civilization had risen before, had been destroyed, had needed rebuilding by survivors who tried desperately to preserve whatever they could from the ruins. The teachers were real, the myths remembered truth, and the catastrophe that made their desperate preservation efforts necessary was written in the geological record, in that black layer of sediment with its nanodiamonds and platinum spikes, and impact signatures that appeared at dozens of sites across multiple continents exactly 12,800 years ago when the comet came and the world ended and everything had to begin again. The resistance isn't random, isn't just scientific skepticism, isn't merely the natural conservatism that makes science slow to accept revolutionary ideas. There's something deeper happening here, something more troubling, something that suggests certain institutions and individuals have decided that some questions shouldn't be asked, that some evidence shouldn't be pursued, that some truths are too dangerous to acknowledge regardless of how compelling the data becomes. The pattern repeats across multiple fronts, across different types of evidence, across various attempts to investigate the Younger Dryas impact and its implications for lost civilizations. Every time researchers get close to something significant, every time evidence accumulates that might force paradigm shifts, obstacles appear, funding disappears, permits get denied, results get dismissed regardless of methodology. The academic suppression operates through mechanisms that are subtle but effective, that don't require explicit conspiracy, that function through shared assumptions and institutional incentives and career preservation instincts that align naturally to resist disruptive change. Journal editors prefer papers that fit within established frameworks, that don't challenge fundamental assumptions, that add incremental knowledge rather than forcing wholesale revision of accepted narratives. Peer reviewers, selected from established authorities in their fields, naturally favor interpretations that support the expertise they've spent careers developing, naturally question results that would invalidate their own previous work, naturally apply higher standards of proof to revolutionary claims than to conventional ones. Grant funding agencies, staffed by scientists who achieved their positions through success within the existing paradigm, naturally prioritize research proposals that build on accepted foundations, that promise results consistent with current understanding, that don't threaten to undermine the theoretical frameworks that justify their own research programs. Graduate students learn quickly which questions are safe to pursue and which will mark them as outsiders, which advisors will support unconventional research and which will steer them toward established paths, which career trajectories lead to success and which lead to marginalization. The system doesn't need conscious conspiracy to suppress uncomfortable ideas, it achieves suppression through structural features that reward conformity and punish deviation from consensus. But sometimes the suppression becomes more direct, more obvious, more difficult to explain through normal academic processes. The Egyptian government's refusal to allow excavation beneath the Sphinx, despite ground-penetrating radar evidence confirming chamber existence, despite Edgar Case's predictions being partially validated, despite the potential for discoveries that could revolutionize our understanding of ancient history, can't be explained through legitimate conservation concerns alone. The blocking of further investigation isn't protecting the monument, isn't preserving it for future generations, is actively preventing discovery of whatever lies beneath, is ensuring that questions remain unanswered and mysteries stay mysterious regardless of available technology and scientific interest. Zahi Hawass, who controlled Egyptian archaeology for decades, who decided which excavations received permits and which researchers gained access to sites, who shaped what the world learned about ancient Egypt through his position as gatekeeper, showed a pattern of behavior that suggested protection of secrets rather than promotion of knowledge. His contradictory statements about the Sphinx shafts and underground chambers, his acknowledgement that they existed followed by denial of their significance, his resistance to independent investigation and his insistence that only approved researchers working under his supervision could study controversial sites, all pointed toward someone managing information rather than facilitating discovery. The same pattern appears with other potentially revolutionary sites, other locations where evidence might force revision of accepted chronology, other monuments that seem older or more sophisticated than conventional dating allows. Gunung Padang in Indonesia, where carbon dating and stratigraphic analysis suggested construction phases extending back 20,000 years, suddenly became off-limits to international researchers after initial results proved too controversial. The Indonesian government, pressured by archaeologists who insisted the dates must be wrong, who argued the site couldn't possibly be that old because it would contradict everything we thought we knew about Southeast Asian prehistory, effectively shut down investigation rather than pursuing the implications of what was being found. academic gatekeepers mobilized to attack Graham Hancock, to dismiss him as a pseudoscientist despite his careful documentation and extensive fieldwork, to ensure that his hypotheses about lost civilizations never received serious consideration from mainstream institutions. The attacks were personal, were vicious, went beyond normal academic disagreement into territory that looked like character assassination designed to ensure no legitimate scholars would associate with him or his ideas. The message was clear, unmistakable, effective: question the established narrative about human origins and face professional destruction, propose that civilizations existed before conventionally accepted timelines and be labeled a fraud, suggest that academic orthodoxy might be wrong about fundamental questions, and watch your reputation burn. The cost of this suppression isn't just delayed progress in one field, isn't merely an interesting hypothesis being prematurely rejected, isn't simply a few researchers being unfairly marginalized. The cost is our understanding of who we are, where we came from, what we're capable of, what we've survived, and how we rebuilt after catastrophe. If the Younger Dryas Impact happened, if it destroyed advanced civilizations that existed before, if survivors scattered and tried to preserve knowledge through teaching less sophisticated populations, then human history is fundamentally different from what we've been taught. We're not the first technological civilization, we're not unique in our achievements, we're not the pinnacle of a steady progression from primitive to advanced, but rather the latest iteration in a cycle that has repeated before and will repeat again. That possibility terrifies certain academics, threatens institutions built on linear narratives of progress, undermines the comfortable assumption that we're smarter than our ancestors, that we know more than previous civilizations, that our technological society represents unprecedented human achievement. If sophisticated civilizations existed 12,000 years ago, if they possess knowledge we've lost, if they built monuments we can't replicate, if they understood astronomy and mathematics and engineering at levels we're only now rediscovering, then our confidence in modern superiority becomes questionable, our assumption that history moves in one direction becomes unsustainable, our belief that civilization is secure and won't collapse becomes doubtful. The implications extend beyond academic pride, beyond institutional inertia, beyond career preservation and funding streams. If the comet came once, if it destroyed civilizations and killed billions and forced humanity to start over, then it can happen again, will happen again, is happening now as we speak in slow motion, as we drift through regions of space that contain debris from fragmenting comets that could intersect Earth's orbit at any time. The Taurid meteor stream, which Earth passes through twice each year, contains objects large enough to cause catastrophic damage, contains fragments from Comet Encke that broke apart relatively recently in astronomical terms, contains potential impactors that we haven't fully catalogued and can't completely predict. Some researchers tracking the Taurid stream have warned that we're entering a period of enhanced risk, that the stream's density peaks on cycles of several thousand years, that we may be approaching or already in one of those peak periods when the probability of significant impact increases dramatically. These warnings get dismissed, get marginalized, get treated as alarmism by authorities who insist our detection systems would provide adequate warning of any dangerous objects. But the same authorities acknowledge we haven't catalogued all potentially hazardous asteroids, haven't tracked all comet fragments, haven't developed systems capable of detecting objects approaching from certain angles or with certain characteristics. The Chelyabinsk meteor of 2013, which exploded over Russia with energy equivalent to nearly 500 kilotons of TNT, which injured over 1,500 people through blast effects and shattered glass, which caught everyone completely by surprise despite all our supposedly sophisticated detection systems, demonstrated how vulnerable we remain to cosmic impacts. That object was only 17 to 20 meters in diameter, tiny compared to the fragments that likely caused the Younger Dryas catastrophe, yet it caused damage across a region encompassing hundreds of square kilometers and would have killed thousands if it had exploded over a major city. Scale that up by factors of hundreds or thousands, imagine dozens of such objects hitting simultaneously across a hemisphere, and you begin to understand what the Younger Dryas Impact might have looked like. We're not ready, not prepared, not taking the threat as seriously as the geological and archaeological evidence suggests we should. The resistance to accepting the Younger Dryas Impact hypothesis isn't just about protecting academic orthodoxy or preserving conventional chronologies or maintaining comfortable narratives about human progress. It's about avoiding uncomfortable conversations about existential risk, about not acknowledging how fragile civilization really is, about pretending we're safe when the evidence clearly shows we're not, when history demonstrates that catastrophes happen and civilizations fall, and sometimes everything has to be rebuilt from ruins. The suppression serves multiple purposes simultaneously, protects multiple interests, satisfies multiple constituencies that would rather not face what the evidence implies. Academic institutions protect their intellectual investments, their theoretical frameworks, their career structures built on assumptions that revolutionary evidence would invalidate. Government agencies protect their authority, their control over narratives about human origins and capabilities, their ability to manage public perception of risk and security. Religious institutions protect their chronologies, their creation narratives, their explanations for human origins that cosmic catastrophes and lost civilizations would complicate or contradict. The public, meanwhile, gets taught a history that's incomplete, gets told a story about human development that ignores critical chapters, gets educated in a framework that makes us feel secure and advanced and in control when the reality is far more precarious. We learn that civilization developed gradually in Mesopotamia, that agriculture was invented around 10,000 years ago, that writing and mathematics and complex social organization emerged over centuries of steady progress. We don't learn that this might be the second or third or 10th iteration of civilization, that previous attempts were destroyed by cosmic catastrophes, that survivors tried desperately to preserve knowledge through dark ages and climate, chaos and social collapse. We don't learn that the monuments our ancestors left behind might be warnings, might be time capsules, might be attempts to tell future generations that catastrophe can happen, has happened, will happen again. We don't learn that flood myths preserved across hundreds of cultures might be actual memories of real events, that stories about fire from the sky and teachers who appeared after disasters might be historical rather than mythological. We don't learn to read the warnings that were encoded in stone, preserved in stories, maintained through oral traditions that academia dismisses as primitive superstition rather than recognizing as alternative forms of knowledge preservation. The black layer lies there still, exposed in excavations across multiple continents, containing its nanodiamonds and platinum spikes and impact signatures, marking the moment when the world ended and everything changed. The evidence keeps accumulating, keeps appearing at new sites, keeps confirming what Firestone proposed in 2007 despite all the resistance and criticism and attempts at refutation. 39 independent research groups have now reported findings consistent with the impact hypothesis, have published in peer-reviewed journals, have used appropriate methodologies and proper stratigraphic controls. The replication that critics claim didn't exist has been achieved repeatedly, has been documented extensively, has been verified by laboratories across multiple countries using different analytical techniques. Yet the mainstream narrative hasn't changed, hasn't incorporated these findings into standard textbooks, hasn't acknowledged that maybe the premature rejection was wrong and the evidence deserves serious consideration. The resistance continues, the suppression persists, the uncomfortable questions remain unasked in polite academic company. The door beneath the Sphinx stays sealed, the chambers stay unexplored, the potential proof of everything stays buried, because authorities have decided that some truths are better left hidden, that some evidence is better left undiscovered, that some questions are better left unanswered. But doors don't stay locked forever, secrets don't remain hidden indefinitely, and suppression can only delay discovery, not prevent it permanently. Technology improves, political situations change, new generations of researchers emerge who weren't invested in the old paradigms, who weren't committed to defending orthodox narratives, who are willing to follow evidence wherever it leads regardless of institutional pressure or career consequences. The truth about the Younger Dryas Impact, about the civilizations it destroyed, about the knowledge that survivors tried to preserve, about the warnings they encoded in monuments and myths, will eventually emerge, will eventually force the revision of human history that evidence has demanded for years. The only question is whether we'll discover the truth in time, whether we'll learn the lessons that catastrophe taught our ancestors, whether we'll take the threat seriously enough to develop proper detection systems and deflection capabilities, and civilizational resilience sufficient to survive what previous iterations couldn't. The comet came before, changed everything, ended civilizations that thought themselves secure. It will come again, the only uncertainty is when, the only variable is whether we'll be ready this time, whether we'll have learned from the geological record and the archaeological evidence and the mythological warnings that were preserved through 10,000 years of oral tradition. The black layer marks a boundary, a moment when one world ended and another began, a warning written in the sediment that we're only now learning to read. The suppression continues, but the evidence keeps accumulating, and eventually the weight of truth becomes too heavy for even institutional resistance to bear. The question isn't whether the truth will emerge, but whether it will emerge soon enough to matter, whether we'll acknowledge the warnings before we need them, whether we'll prepare for catastrophe while we still have time, rather than discovering too late that our ancestors tried to tell us something and we weren't listening.